Hello, and welcome to Simply Earth, where curiosity thrives and science unhurries. Whether you're getting ready for bed or just letting your mind wander a bit before sleep, I'm glad you're here. Tonight, let's pursue a question.
Not one with easy answers or clear boundaries, but one that invites us to rethink the land beneath our feet. What if Earth was designed?
The news editorial team notes that this isn't about Earth being picked off a shelf or assembled like a flat-packed bookcase. While the idea of tiny space instruments is admittedly fun to imagine, it's about a broader idea. What if Earth wasn't simply the result of random events and blind physics, but something shaped intentionally, methodically by some force or process?
Whether you envision this as an intelligent designer, a complex simulation, a vast natural algorithm, or something else entirely is up to you. The point is, we're going to explore this not as a debate, but as an exploration.
In this context, there will be no loud opinions, only quiet questions. And we won't rush to answers. That's not the pace we're pursuing here. Instead, we'll take a slow stroll through the landscape of this idea, noticing small details and larger patterns.
And perhaps along the way, we'll discover that even asking the question opens up new ways of seeing the world, ways that are just as important as the answer, if not more so.
To begin, let's start small, not with physics or philosophy, but with the simple personal experience of looking around. Think about your typical day. You wake up to light streaming through the window, not too hot, not too cold. You breathe in the air. Your body is perfectly designed to use. You're thirsty, and water, clear, tasteless, essential, awaits you. Perhaps you step outside. Plants, animals, the sky, the temperature, gravity. Everything seems to align just right to make life not only possible but comfortable. It's easy to take this for granted. Most of us do. But beneath this comfort lies something worth pondering. Is it all coincidence? Could it be? Or is it arranged like puzzle pieces that simply fit together too well? Of course, science has offered a detailed, well-developed account of the early solar system, planet formation, chemical evolution, and so on. The news editorial emphasizes that there is a wealth of information about the early solar system, planet formation, chemical evolution, and so on. We built models, collected data, and traced timelines spanning billions of years. It's a solid foundation. And yet, even within this framework, there are things that give people pause, things that seem, frankly, a little too convenient. The Earth orbits a very stable star. It does so in a range often called the habitable zone. A zone where water can exist in liquid form, which turns out to be quite important for life as we know it. This alone might seem fortunate, but it goes further than that.
The tilt of the planet, which gives us seasons, the speed of its rotation, which prevents temperatures from fluctuating much, the size of the moon, which influences the tides and stabilizes this tilt, the presence of a magnetic field, which protects us from solar radiation, the mix of gases in the atmosphere, the balance of land and ocean. The newsroom also reports that one could go on and on. Each of these things could have been different, radically different, and if so, life as we know it might never have emerged. Some call this the anthropic principle.
The idea that, of course, the universe appears adapted for life because we are here to observe it. If it weren't adapted for life, we wouldn't be here to ask these questions.
In a sense, this is a neat explanation, but it doesn't stop the wonder. Is it really enough to simply say, well, we're here, so it all happened somehow? Or is that avoiding something deeper? None of this proves design. That's important to say. Patterns don't prove purpose, but they can point to one, or at least force one to be considered. So what we're going to do is look at these patterns not as believers or skeptics, but as explorers.
We'll wander through clues and coincidences, physics and philosophy, mathematics and metaphors. And we'll do it slowly, without necessarily reaching a single conclusion. Because whether the Earth was designed or not, it behaves as if it were. That's not a statement.
It's simply an observation, an invitation to ask what would be different if it were designed? What would remain the same? To explore this, we need to go wide and deep.
The news editorial team will explore planetary physics, biology, and chemistry, and will also touch on issues of perception and narrative, exploring why humanity is so drawn to the idea of a world designed with purpose.
This fascination may be rooted in religious beliefs, but it's not limited to them. The urge to gaze at the heavens and sense that they hold special meaning arose long before the advent of sacred books and temples.
Perhaps this quality is ingrained in our very nature. Take, for example, our interaction with symmetry. We are invariably drawn to symmetrical objects, faces, flowers, shells, galaxies. When we see symmetry, our brains activate, evoking a sense of harmony and rightness.
This inclination isn't proof of anything, but it does serve as a starting point for reflection. Why does a universe shaped by chance continue to bestow order upon us? Why does our sense of beauty so often align with what appears to be efficient, functional, and mathematically elegant? In considering this question, it's worth noting that humanity interacts with symmetry at a profound level.
An attraction to symmetrical forms, whether in faces, flowers, shells, or galaxies, evokes a positive response in our brains. This preference for order and harmony in the world raises fundamental questions about the nature of the universe and its connection to our perception of beauty.
Perhaps this inclination toward symmetry reflects deeper patterns inherent in creation, pointing to the existence of structure and order beyond randomness. Humanity has always sought patterns and meaning in the world around us, and an attraction to symmetry may be one manifestation of this age-old desire to understand the structure of the universe. Exploring these questions allows us to delve deeper into our understanding of both our own perceptions and the fundamental principles underlying creation. This is where things get interesting, because even with a purely scientific approach to the worldview, we inevitably encounter questions with philosophical overtones. The more we learn about biology, the more we realize how finely tuned many systems are. From the way proteins fold, to the way DNA stores information, and the way cells communicate. All of these systems are characterized by precision, interdependence, and in many cases, inexplicable efficiency. Of course, this isn't to say everything is perfect. Evolution is a complex process, and organisms are full of peculiarities and vestiges. Yet it works surprisingly well, sometimes resembling what we might call a blueprint.
It's worth noting that humanity constantly confronts philosophical questions, even with a strict scientific approach. Biology, for example, reveals the incredible fine-tuning of various systems.
From the complex structure of proteins to the way DNA stores information and the interactions between cells, all processes are characterized by precision, interdependence, and astonishing efficiency.
Although evolution doesn't always lead to ideal solutions, and many illogical and redundant elements can be found within an organism, the overall functionality of the organism remains astonishing.
This efficiency and organization in nature sometimes resembles a kind of design, raising questions about the possible causes of such structure and whether it is the result of chance or the consequence of deeper patterns. Reflections on biological systems and their astonishing complexity lead to philosophical questions about the nature of life, the structure of the universe, and humanity's place in it. The concept of design can be ambiguous. It often conjures up images of a conscious being creating blueprints or tinkering with molecules. However, design doesn't necessarily imply that. It can imply structure, intention, or pattern that arises not by chance, but with purpose.
Even if we don't know the source of this direction, the idea that Earth is designed doesn't require a specific designer. It could mean something more abstract, like a universe governed by deep logic that randomly produces life-supporting outcomes, or something else entirely.
It's also possible that Earth wasn't created from scratch, but was chosen. Out of many possible worlds, this one proved suitable for supporting life, and so here we are. But that raises another question. How many potential Earths are there?
Are we the one lucky one in a trillion? Or is the universe teeming with other worlds like ours, each with its own version of stability and strange beauty? At this point, we don't know. But as we discover exoplanets, and thousands have already been discovered, we're beginning to understand just how rare or common Earth-like conditions can be. Right now, nothing compares to what we have.
We're finding planets that are too hot, too cold, too big, too dense, too irradiated, or too young. Planets without atmospheres, planets with too much gas, planets orbiting stars that flare violently. The more we search, the clearer it becomes that Earth is unusual.
It's not impossible, it's not unique, but it's definitely not average. However, the concept of average is difficult to define in a universe of this scale. Perhaps the rarity of Earth-like conditions is precisely what we would expect in a system governed by chance.
Or perhaps it points to something else. Either way, it encourages us to keep asking questions. Another interesting aspect to consider is timing. Not just space, not just location in the galaxy, but also timing. Life needed more than just the right ingredients. It needed the right sequence of events. A stable planet, yes, but also billions of years of relatively calm space weather. Not too many asteroid impacts, not too many solar flares, a moon to stabilize, tectonic activity to recycle carbon, an atmosphere that gradually changed just the way life needed to evolve. The timing had to be just right. It's not impossible, but it's another piece in the growing puzzle. People have tried to explain it in different ways. Some see divine providence, others luck, still others inevitability, given enough time and space. However, the idea that the Earth could have been deliberately designed, either directly or through some deep structure of natural laws, remains compelling not because it can be proven, but because it continues to resonate with our lived experience.
We are creatures who build, who plan, who imagine outcomes before they happen. So when we look at a world that seems designed precisely as it should be, it's natural to wonder whether someone or something planned it. However, we need to be cautious.
Patterns can arise from chance. Perception can be misleading. Just because something appears designed doesn't mean it is. Just because something is unlikely doesn't mean it was planned. But the converse is also true. Just because science can explain how something happened doesn't mean we fully understand why it happened or whether there's a deeper structure behind it. So the question we explore isn't about disproving science or proving faith. It's about creating a space where both can ask the same question from different perspectives. What if Earth was designed? What would change? What would remain the same?
And what, if anything, does this mean for how we live, how we see each other, and how we move forward? As we continue, we'll begin to consider specific aspects of Earth that frequently arise in this conversation. its optimal orbital position, the extraordinary role of the Moon, the remarkable balance of its atmosphere, the strange details of DNA, the numerous systems that must have aligned for intelligent life to emerge. Each of these aspects opens its own set of questions, not just about science, but about what we expect from reality itself. When we ask whether Earth was designed, we're not simply asking a question about planets or physics. We're tapping into something deeper. This question, despite all its scientific and speculative implications, is actually deeply personal. It concerns how we understand our place in the universe. Do we view life as an accident that just happened, or something more intentional? Do we see the world as a series of coincidences, or as part of something that was meant to be exactly the way it is? That's why this idea differs from other scientific topics. If you ask how volcanoes form or why the seasons change, it's interesting but not emotional. But when you ask whether it's possible that the Earth was created intentionally, you're entering into a much older conversation, one that dates back to a time before telescopes or textbooks. You're asking a question that people have been asking since they first looked at the stars and wondered what all this was for. It's the same question that surfaces in philosophy, in religion, in mythology, stories of the earth shaped by hands, spirits, or voices that spoke the world into existence. And while many of these stories diverge in detail, they share something essential. They reflect a human instinct, the urge to connect what is with what means, to transform facts into purpose. This instinct should not be discarded. It's easy to assume that science and meaning is separate, that one tells us how and the other why, but the line isn't always so clear. The more we understand how the universe works, the more we notice moments when structure and outcome seem to converge in a way that feels, for lack of a better word, manageable. Take something as simple as carbon.
Life on Earth is fundamentally built around this one element. Carbon forms the backbone of DNA, proteins, and all the complex chemistry that makes cells work. It's incredibly versatile, bonding easily, forming long chains, creating stable molecules that can carry information and build structures.
Without it, life as we know it simply wouldn't work. And when you look at how stars create elements, you realize that carbon itself is the product of a very narrow set of conditions. If the physics of fusion had been even slightly different, just a little stronger or weaker, the universe might have been full of hydrogen and helium, but without carbon, there's no life, no us.
This coincidence makes people stop and think, not because it proves anything, but because it shows how specific things had to be. And the more we learn about the laws of physics, the more it seems that many of these quantities, mass, charge, gravity, the strength of forces, had to be within very narrow limits for complex matter to exist at all.
Not just life, but stars, planets, chemistry. This is sometimes called fine-tuning. And this raises a question that's been quietly lurking beneath much of modern science. Why these particular numbers? Why this particular version of reality? There are ways to explain this. One is the multiverse, the idea that perhaps there are countless universes, each with its own set of physical constants, and we just happen to be in the one where everything lines up. That might make sense.
But we don't have any direct evidence for other universes, not yet. And even if there were, that still wouldn't tell us why our universe exists the way it does. It just pushes the question back a step.
Another idea is that perhaps these values aren't chosen at all. Perhaps they're simply embedded in some deeper structure we haven't yet discovered. But that's still a bit of a mystery, since either way, we're confronted with a reality where things were meant to be a certain way, and they are.
And then, inevitably,
you come to a deeper version of the question. It's not just why the Earth is the way it is, but why is anything the way it is? Why are there laws of physics at all?
Why must there be a universe with rules, structure, patterns, and matter? Why must there be something rather than nothing? It's a question no telescope can answer. And yet, we keep returning to it.
What's important to say now is that science doesn't need a purpose to work with. You can study gravity without believing it was created. You can decode DNA without asking who wrote it. But science doesn't forbid these questions. It simply doesn't depend on them.
And for some people, that leaves room for a kind of middle ground, a place where you can explore the world through evidence and still leave room for the possibility that there's something more going on than we can measure.
This is where design comes into the conversation, not as a replacement for science, but as a perspective, a lens. It's not saying we should stop asking questions when something seems fine-tuned. It's saying that the fine-tuning itself is worth exploring. And maybe, just maybe, it points to something deeper. Of course, not everyone agrees on what that deeper something might be. Some people imagine a conscious designer, a god, an architect, a being with intentions. Others imagine a kind of embedded intelligence in the universe. Not a person, but a process that naturally strives for order, beauty, or complexity. Others see design as a human projection, something we impose on the world because we are programmed to find patterns and stories.
In each of these perspectives, the question is the same, but the answers differ. Despite this, the question remains. It sits quietly beneath everything we do.
Every scientific discovery, every new satellite image, every equation or theory, all of it is framed by the strange fact that we are looking at it, that there is something to look at, and that it behaves in a way we can understand.
Think about that for a moment. Not just that the world exists, but that it is comprehensible, that we can measure it, predict it, explain it.
That our brains, which evolved from ancient nervous systems designed to find food and avoid danger, can now model galaxies, build computers, and ask whether the universe has a purpose.
Why should the mind of a species on a small rock in a remote corner of the galaxy be able to understand the rules that govern space and time? Again, this proves nothing, but it is strange.
It makes us wonder if our ability to understand the universe is itself part of some larger pattern, whether the universe is not only structured, but structured in a way that invites understanding. This is not a statement, but simply a thought.
Ultimately, these questions are not meant to be threatening. They take nothing away from science. If anything, they show how science can take us right to the edge of mystery and then keep going. You don't need to answer every question for it to matter.
Sometimes, simply holding the question is enough.
And this idea that maybe the world was built, arranged, or shaped in some way is one of the oldest questions we have. But it's also one of the most modern because we now have the tools to look more closely than ever before, to examine the building blocks of matter, the forces of nature, the dynamics of life.
And as we do, the question only deepens. Not because we run out of explanations, but because the explanations themselves are so detailed, so precise, and so delicately balanced that they give you pause.
They make you think, did all of this just happen to work out, or was it meant to happen? We can't answer that completely, not yet, maybe never, but we can keep asking.
We can keep following the structure, the order, the logic, not to prove anything, but to understand and, perhaps in the process, get a little closer to what underlies it all. When we begin to look closely at the Earth itself, not just its place in the cosmos, but its surface, its systems, the everyday materials beneath our feet, we begin to notice certain patterns.
Some are geological, some are chemical, some are mathematical, and some are structural. And the more we zoom in, the more these patterns can begin to seem strangely intentional. It all starts with the fundamentals.
Our planet orbits a star we call the Sun and is located at the perfect distance from it for liquid water to exist on the surface. Water covers over 70% of the surface, forming vast oceans that regulate temperature and climate.
The air we breathe is a mixture of gases ideal for animal life, with just the right amount of oxygen for breathing and a layer of ozone to protect against harmful rays. And then comes the geology.
The planet is layered like an onion, with a molten core that creates a magnetic field that protects us from cosmic radiation. On top lies the mantle, a thick layer of hot rock that slowly flows and churns, causing volcanoes and earthquakes, but also renewing the Earth's surface and creating new land. Finally, there is the crust, a thin outer shell, broken into pieces that move and collide, forming mountains, valleys, and ocean trenches. The Earth itself seems designed with life in mind. But that's just the beginning. Then comes the chemical elements.
Everything we see and touch is made of atoms, tiny particles that combine to form elements like hydrogen, helium, oxygen, and carbon. The universe contains about 92 different elements, from the lightest to the heaviest, each with its own unique properties.
But here's the weird part. Living things like us are primarily made of just 6 elements: oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. These 6 elements make up 97% of our body mass. Why these 6 elements? What's so special about them?
Well, it turns out that these elements have a number of unique properties that make them ideal for life. Carbon, for example, can form long chains and complex structures, making it the basis of organic molecules.
Hydrogen is the smallest and most abundant element in the universe and can easily combine with other elements. Oxygen is highly reactive and can release energy when burned, making it essential for respiration. And nitrogen is inert and can stabilize organic molecules. Together, these 6 elements form the building blocks of life. They create the proteins, carbohydrates, fats, and nucleic acids necessary for all known living things. The Earth's crust, for example, is divided into plates. These plates float on the hotter, softer mantle, shifting over time.
This shifting creates mountains, earthquakes, volcanoes, and even oceans. Without plate tectonics, the Earth's surface would likely be flat and static. Erosion would destroy it. Nutrients would not circulate. Life as we know it might never have flourished.
The movement of plates also plays a role in carbon regulation. When volcanoes erupt, they release carbon dioxide. When mountains weather, they release carbon dioxide back down. This balance influences climate, which in turn shapes the entire biosphere.
This is a process that science has now studied in great detail. But when you look at it from a wider perspective, it's hard not to wonder how many ways this system could have failed. The planet didn't just need a solid crust.
It needed one that cracked, floated, and moved. If the crust were too thick or the mantle too rigid, the plates wouldn't move. If it were too active, the surface would be constantly remade, leaving no time for life to stabilize.
Somehow, Earth ended up somewhere in between, not too calm, not too chaotic. The more we look at how things work, the more the idea of a happy medium emerges. Soil, for example, is a mixture of minerals, organic matter, water, and air.
But the ratio has to be just right. Too much sand and water drains too quickly. Too much clay and roots can't breathe. The best soils, the ones that support forests, crops, and ecosystems, maintain a delicate balance.
This balance may vary by region, but it always falls within a narrow range of properties. Plants evolve to fit these conditions, or perhaps vice versa. It's a theme that comes up often. Co-evolution.
Not just plants and soil, but also insects and flowers, fungi and trees, bacteria and animals. Systems that not only work, but work together. Each part is shaped by the presence of the other. And sometimes the fit is so precise that it begins to feel more like cobbling together than adaptation. Consider something as mundane as a seed. It contains everything it needs to grow: instructions, energy, structure.
It waits in the soil, responding to moisture, temperature, and light. When these conditions are right, it transforms. Roots reach down, stems reach up. It's a process we can describe in biological terms, but the timing, sensitivity, and precision are astounding.
Even the shape of the seed, the way it moves, sticks, sinks, or floats, seems optimized. Not perfect, but highly efficient. It's easy to see all of this as the result of natural selection. Traits that worked survived. Traits that didn't disappear.
But selection works on what's available. It doesn't build from scratch. It repurposes, tweaks, prunes. So starting materials matter. And when we look at those starting materials, the building blocks of life, carbon, nitrogen, oxygen, hydrogen, they're not just common. They're extraordinarily versatile. They bond easily. They store energy well. They form the right kind of molecules, the ones that twist, curl, and replicate. Some of this may be chemistry, but chemistry also follows rules. And these rules in our universe seem to favor complexity. That doesn't mean complexity is inevitable.
But it does mean that once it gets going, it has room to grow. And Earth, for some reason, seems to have given it a head start. Take water. It's not a metal, not a gas, and not a particularly rare compound.
But it has a list of unusual properties. It expands when frozen, meaning ice floats, a rare trait that allows life to survive beneath frozen lakes. It has a high specific heat capacity, which stabilizes temperatures. It dissolves more substances than almost any other liquid, making it an ideal medium for chemical reactions. All of these properties are simply perfect for life, and they all stem from the angle between two hydrogen atoms and an oxygen atom. If this angle was slightly different, water would behave completely differently, and so would everything dependent on it. Then there's the idea of fractals, patterns that repeat at different scales. You see them in river networks, mountain regions, coastlines, tree branches, blood vessels. These aren't just pretty shapes, they're efficient. They move resources over large areas with minimal material. Trees send nutrients from the roots to their leaves using fractal branching. Our lungs do the same with air. These shapes aren't random. They follow specific mathematical rules. Some call these laws convergence, which constantly emerge independently in different systems. Others see it as more deliberate. Another example is the Fibonacci sequence, a spiraling pattern found in shells, pine cones, sunflowers, and galaxies. It's not universal, but it's common and often appears where growth occurs. This is because it allows for efficient packing and expansion. Again, there's a mathematical reason behind it, but the very fact that mathematics appears in biology is worth pondering.
Living things, shaped by blind processes over millions of years,
often conform to principles we find elegant or logical. This raises a strange question. Does the universe follow mathematics because it must?
Or does mathematics describe it so well because they both stem from the same source? This isn't just a philosophical puzzle. It has real implications for our understanding of structure.
Because if life emerges from patterns and those patterns obey rules, then where do those rules come from? This is where the idea of blueprints comes in. Not in the literal sense of someone drawing up diagrams, but in the sense of consistent systems that create results.
The Earth isn't random, and it's not purely chaotic. There's order here, a kind of layered functionality. From the chemistry of the soil to the movement of the planets, everything behaves in a regular, testable, and repeatable way. That's what science is based on.
But it also makes people wonder if this pattern points to something beyond it. Patterns can emerge from chaos. That's true. We've seen this in models and simulations, but these patterns often require very specific initial conditions. Tweak them slightly, and the outcome changes completely.
Which makes you wonder, what were the initial conditions here? Why these laws? Why this structure? Why is there a world where minerals form crystals, plants respond to light, and animals can develop eyes? This doesn't mean there's anything supernatural going on.
But the more we study the structure of the Earth, the blueprints in its soil, its systems, its cycles, the more often the question returns, could this have been designed? Not by magic or miracle, but by a process we don't yet understand.
A process that involves design, not as a product of choice, but as a principle, a natural tendency in life-supporting systems. We don't have to decide this now. We're not here to answer, only to notice.
And what we noticed is that the Earth is not a random mixture of things. It's a deeply interconnected system, full of rules, balances, and alignments that seem to gravitate towards stability, growth, and sustainability. This doesn't mean it's perfect, far from it.
But it works, and it works in a way that seems strangely attuned. When people talk about why life exists on Earth, not Mars or Venus, they often mention the so-called Goldilocks zone. This nickname refers to the region around a star where the temperature is just right, not too hot and not too cold for liquid water to exist. And since water seems essential for all known life, it's assumed that any planet comfortably located within this zone has at least a chance of survival.
Earth lies right in the middle of this range, close enough to the sun to avoid freezing, and far enough away to avoid boiling. The sun itself is stable and long-lived, giving the planet billions of years to develop complex ecosystems.
It's easy to hear this and feel a kind of satisfaction, as if the universe played a very specific game of darts and hit the bullseye. But, as usual, the closer you look, the more complex it becomes. The habitable zone isn't fixed. It depends on the size and brightness of the star. For smaller and less luminous stars, the Goldilocks zone is narrower and closer. For a larger, hotter star, the zone extends further.
This may seem like a small matter, but each situation brings its own complications. Smaller stars are prone to flares, emitting torrents of radiation that can strip a planet of its atmosphere.
Larger stars burn through their fuel faster, meaning less time for life to develop. It turns out that Earth's sun is almost average, stable, bright, and long-lived.
It may not be the only type of star that can support life, but it's one of the best. Then there's the orbit. Earth isn't just at the right distance, it stays there. Its path around the sun is nearly circular.
This means the amount of solar energy it receives doesn't vary much throughout the year. Some variation is beneficial, It's what gives us seasons, but too much could provoke climate fluctuations between extremes.
A slightly more elongated orbit could make the planet uninhabitable over large regions. And yet here we are, with a wobble that's not too extreme and a tilt that's just enough to stir things up without upsetting everything.
Still, distance and orbit are just the beginning. A planet can be in the habitable zone and still be completely barren. Just look at Mars. It's on the outer edge of the Goldilocks zone. It has ice.
It may have had water in the past, but now it's dry, cold, and susceptible to radiation. That's because its magnetic field has collapsed, and with it, most of its atmosphere. No shield, no pressure, no heat, no protection.
The ingredients were there, but the kitchen fell apart. Venus is at the other end, just inside the inner edge of the habitable zone. It's about the same size as Earth, and has a similar composition, but its atmosphere is saturated with carbon dioxide, creating a runaway greenhouse effect.
The surface temperature is hot enough to melt lead. Its clouds are made of sulfuric acid. If Earth is a warm cup of tea, then Venus is a boiling kettle that never stops screaming. This puts Earth in a very small window.
Not just in terms of distance, but also in terms of how its systems work together. Its atmosphere is thick enough to retain some heat, but not too much. It contains oxygen, nitrogen, and carbon dioxide in just the right proportions.
Its oceans moderate the climate. Its weather systems distribute heat across the globe. The greenhouse effect exists, but it's not out of control. It's not a delicate balance at this point, definitely. Rather, it's dynamic. Everything is changing, adapting, compensating.
When one thing changes, other parts respond. This flexibility is part of what makes the system stable. But then again, it didn't have to be this way. Minor differences in early conditions could have resulted in the planet that looked very different.
And if you rewind far enough, you can reach the formation of the solar system itself, the swirling cloud of gas and dust that gave birth to the sun and its planets. Within that cloud, where Earth ended up was determined by a combination of gravitational fields, collisions, and leftover material. It could have formed further away, where it would have been a frozen rock.
It could have formed closer, where it could have ended up like Mercury, but neither happened. It formed here, in a zone where water could remain liquid and life had the time and conditions to begin.
Some see this as a fluke, the result of many rolls of the cosmic dice, and that's a perfectly reasonable view. But others look at the outcome, a planet with the right temperature, the right chemistry, the right history, and wonder if the dice were rigged.
Not in a cheating or unfair way, but in a way that suggests direction, perhaps unintentional, but not indifferent either. This line of thinking leads to new questions. Is the Goldilocks zone unique or common? Do other stars have planets in the right range?
As it turns out, yes, at least in theory. Thousands of exoplanets have been discovered, and quite a few are in the habitable zone of their stars. But we still know little about them. We don't know if they have atmospheres, water, or magnetic fields.
We don't know if their climate is stable or harsh. We don't know what's going on beneath the surface. And even if one has the right ingredients, we don't know whether those ingredients formed life or whether life ever had a chance.
So, Earth remains our best example, and the more we study it, the more finely tuned it seems. It's not perfect. Climates can change, natural disasters can occur, ecosystems can collapse, but overall, balance holds. Life goes on.
And not just simple life, complex life, conscious life, life that asks questions about how it all came to be. The phrase just right
may sound simple, but it's not. It involves hundreds of interacting systems: geology, weather, magnetism, chemistry, biology, all behaving in a way that supports the presence and continuity of life. It's not just the location, but everything that location allows. And yet, that might not be enough to prove anything.
Perhaps it's a happy accident. Perhaps life is rare, but not impossible, and Earth is simply one of those cases where everything fits. That's the standard scientific view.
But there's also a quiet, insistent feeling, not a conclusion, but a sense that this coincidence transcends probabilities. The newsroom believes that all of this reflects something deeper about how the universe functions, or should function.
If we assume there is a design, what would that design be seeking? Perhaps toward life, complexity, or simply balance, toward a system that maintains its integrity long enough to become interesting. This doesn't mean everything is perfect or easy.
Earth is not a utopia, but it is unusually well positioned for the emergence of something rare and complex. Once you start looking beyond Earth's location and focus on what Earth is, the structure of the planet itself becomes part of the story. Not just the surface or the land we walk on, but the entire layout, from its iron core to its shape of its orbit. If Earth was designed to support life, then one would expect this structure to be part of the plan.
And even if it wasn't designed in any purposeful way, the arrangement of its parts still raises some interesting questions. Much of this begins at the center.
Earth's core is composed primarily of iron and nickel and is divided into two parts, a solid inner core and a liquid outer core. The movement of this outer core is responsible for creating Earth's magnetic field, which protects the surface from solar and cosmic radiation.
Without it, the planet would be constantly bombarded by charged particles that could strip its atmosphere, damage its DNA, and make life significantly more difficult, if not impossible. This magnetic field doesn't just exist, it is generated by a process called the geodynamo.
The Earth's rotation causes the lipid metal to swirl, and these movements generate electric currents, which in turn create a magnetic field. For this system to work, several conditions must be met. You need the right materials.
You need a certain amount of internal heat, which comes from radioactive decay and residual energy from the planet's formation. You need a certain size, because small planets cool too quickly. You also need rotation, but not too much.
The Earth rotates once every 24 hours, which is fast enough to keep the core moving and stable enough to not cause chaos on the surface. It's easy to take this for granted, but change any one of these elements. Make the planet a little smaller, a little slower, a little less metallic, and the entire magnetic system can fail. That's exactly what happened to Mars. It likely had a magnetic field early on, but it cooled too quickly.
The core stopped rotating, and the shield disappeared. This was followed by a slow loss of its atmosphere and surface water. Above the core is the mantle, which slowly moves over time, setting in motion the tectonic plates on the surface.
These plates, as we discussed earlier, are crucial. They help recycle minerals, form continents, build mountains, and regulate the carbon cycle. But they also require a certain amount of heat and a delicate balance between rigidity and movement.
If the mantle were too soft, the crust would constantly erode. Too rigid, and nothing would move at all. The Earth seems to have settled on just the right setting. It is dynamic, but not unstable. Over time, continents drift, collide, break apart, and reform.
This movement alters the climate, creates new habitats, and helps isolate ecosystems, which is a key driver of biodiversity. It is also part of the reason why so many different forms of life have evolved in different regions.
Without this movement, the planet's surface might be uniform and stagnant. Even the crust itself plays a role. It's thin compared to the rest of the planet, just a few kilometers deep beneath the oceans, slightly thicker beneath the continents, but it's where all surface life exists.
The composition of this crust is rich in the elements essential for life: carbon, phosphorus, sulfur, calcium, potassium. These elements didn't all come from Earth's primordial materials.
Many arrived during a phase called the Late Heavy Bombardment, when asteroids and comets delivered organic molecules, water, and other building blocks. This event could have played out very differently. Too many impacts and the surface might never have cooled.
Too few, and the planet might not have had the ingredients necessary for life. Instead, Earth seems to have gotten just the right amount. A mix of rocky and icy objects added to what was already there.
Another moment when things weren't supposed to match, but somehow did. Outside all of this is the atmosphere, which acts as both a barrier and a support system.
It keeps the planet warm, protects it from smaller space debris, and contains the gases necessary for respiration and photosynthesis. Initially, things were different. The early atmosphere was likely rich in carbon dioxide, methane, and ammonia.
This mixture was toxic to modern animals, but beneficial to early microorganisms. Over time, photosynthetic organisms began producing oxygen, which ultimately transformed the atmosphere into what we add today. This change, known as the Great Oxidation Event, could have gone either way.
Oxygen is a reactive element. It can be harmful in high concentrations, but in the right amounts, it facilitates complex metabolism, which in turn supports multicellular life.
The fact that Earth's systems did not collapse under the stress of this shift is another example of how feedback loops, both positive and negative, kept everything within certain limits. The balance between carbon dioxide and oxygen is still maintained by living systems.
Forests, oceans, and soil act as carbon sinks. Volcanic activity and respiration return gases to the mix. The result is not a perfect equilibrium, but a system that self-regulates, at least over long periods of time.
In this sense, the Earth's surface is less like a machine and more like a living organism, sensitive, flexible, always adapting. And then comes water. Its distribution is uneven, but effective.
About 70% of the surface is covered by oceans, which help regulate temperature and circulate nutrients. Fresh water exists in rivers, lakes, ice, and underground aquifers. This mixture supports both marine and terrestrial life.
And it relies on a planetary system of rain, evaporation, and flow, which is linked to both geography and solar energy. Even the planet's tilt of roughly 23.5 degrees determines how sunlight reaches different regions, creating seasonal cycles.
This tilt is stabilized by the moon, which we'll examine in more detail later. Without it, the tilt could fluctuate chaotically, causing wild climate changes over short periods.
Instead, we get a reliable rhythm to which life has adapted. Migrations, hibernation, flowering times, all linked to the angle of sunlight and the arc of the year.
Put all these pieces together and you get not a simple object in space, but a complex, multi-layered system, one that generates its own magnetic field, regulates its own temperature, cyclically utilizes its own resources, and hosts its own life.
A planet that creates the conditions it needs and maintains them through feedback and flow. None of this proves anything beyond what we observe, but it opens up a different way of looking at it.
Instead of seeing Earth simply as a fortunate combination of features, you can begin to see it as something with an internal logic. Not a logic necessarily imposed from without, but a logic that leads to life-sustaining results.
Whether this logic is built in, emergent, or exists as part of some broader structure is a question we still revolve around. For something that hangs in the sky every night, the moon is a bit of an oddball. It's large compared to the planet it orbits. Its gravitational pull is strong enough to affect the oceans, and its role in Earth's stability is more than just a side effect.
It may be one of the most important factors in why life has survived here for so long. On the surface, the moon appears to be a natural satellite, a product of whatever forces shaped the solar system.
But when scientists began to look more closely, they realized its presence was more complicated to explain than first appeared. The leading theory is that the moon formed as a result of a massive impact.
A Mars-sized object, often called Theia, is thought to have slammed into the early Earth. The impact would have ejected a huge amount of material into orbit, which then coalesced into what became the Moon.
This theory explains why the Moon's composition is so similar to Earth's outer layers, and why its orbit is relatively close and stable. It also fits with models of how the early bodies of the solar system formed and interacted.
But this explanation depends on a very specific set of circumstances. Theia had to be large enough to knock material into orbit, but not so large as to destroy the Earth entirely.
The impact angle had to be just right, a glancing blow, not a direct hit. The material had to coalesce, not disperse, and the system subsequently had to settle into a stable orbit that would last for billions of years.
This is a narrow window of opportunity. A slight increase in velocity, a minor change in trajectory, and Earth could have been left without a moon at all, either with a chaotic ring of debris or an unstable secondary body that would eventually collapse back into itself.
But that didn't happen. Instead, we got one large moon, one that rotates in sync with its orbit, always showing the same face to Earth, and orbits at the right distance to have a significant impact without destabilizing the system.
It turns out that this influence is significant. First, the Moon plays a crucial role in stabilizing the Earth's axial tilt. Without it, the planet's tilt could fluctuate wildly over time, shifting between near-zero and extreme angles. Such fluctuations would cause widespread climate change.
Seasons could become unpredictable or even disappear. Regions that are currently temperate could freeze or overheat only to return to their original state again. Such environmental instability would significantly hinder the adaptation and long-term survival of ecosystems. The Moon's gravitational pull also causes tides.
Tides move nutrients in coastal ecosystems, help regulate temperature in shallow water, and may have played a role in the origin of life by creating wet and dry cycles that facilitate chemical reactions.
The ebb and flow of the oceans are more than just background motion. They shape coastlines, influence weather patterns, and influence the behavior of countless species. There is also a sudden effect of time.
The Moon's influence on Earth's rotation causes the planet to gradually slow down. A few billion years ago, a day on Earth was much shorter, about 6 hours. Over time, tidal friction extended it to the 24 hours we know today.
This process is still ongoing, albeit at such a slow rate that it's impossible to notice it within a human lifetime. Nevertheless, the long-term effect was a slowing of rotation, which likely contributed to the planet's climate stability.
And then there's light, not in the mystical sense, but in the biological sense. Many organisms use the lunar cycle as a clock, coordinating migration, reproduction, feeding, and sleep patterns. Coral reefs spawn according to moonlight. Insects navigate by it.
Even some predators and prey adjust their activity depending on how bright the night is. The moon creates a rhythm that many life forms have ingrained into their biology. All this from an object that, by some estimates, shouldn't even be there.
Statistically, large moons like Earth's are rare among the rocky planets. Mars has 2 small irregular moons, likely captured asteroids. Mercury and Venus have none. In our current understanding of planetary formation, large moons aren't a guaranteed outcome. They're unusual. And yet, Earth has one.
And not just any moon, but one that seems almost tailor-made for the job. That's what keeps raising the question. Not because anyone thinks the moon was placed there with tools or blueprints, but because the result, a stable life-supporting planet with a stabilizing satellite, is unusual enough to warrant notice.
The moon's formation, its orbit, its impact, all add another layer to the question of how Earth acquired such peculiar properties. Some argue that even if the moon hadn't formed, life might still have arisen in some form.
It's possible, but complex multicellular life would have a harder time surviving in a more chaotic climate, and the long-term evolution of intelligent organisms would be far less likely without stable conditions. Adapting to seasonal changes is one thing.
Dealing with a tilt that varies dramatically over tens of thousands of years is quite another. If we look at the moon purely as a random outcome, it's a remarkable result. If we look at it as part of a larger structure, it's another element that fits surprisingly well. Either way, it's part of the system that makes Earth what it is. There are also more speculative ideas about the moon.
Some suggest it could have helped protect Earth from asteroid impacts by altering the trajectory of incoming objects. Others believe its presence could have affected the distribution of heat within the Earth's core, influencing the geodynamo that powers the magnetic field.
These theories are more difficult to prove, but they point to a growing awareness that the moon is more than just a passive companion. This is an active part of Earth's history.
And even now, it continues to move, slowly moving away from Earth at about 4 centimeters per year. This change is insignificant on a human scale, but over a geologic time, it accumulates.
In a few billion years, total solar eclipses, when the moon perfectly blocks the sun, will cease. The moon will be too far away to appear the same size in the sky, making this current position, like so much else on Earth, part of a limited period of time.
Not forever, but long enough to matter. Most of the time, gravity goes unnoticed. It's always present, always at work, but almost always ignored. You don't notice it until something falls, until you step on a scale, or until your coffee tips over and reminds you that even invisible forces always win.
But in terms of shaping the planet and holding everything on it together, gravity is more than just background. It's structure beneath structure. Gravity is not a strong force, not by the standards of physics. Compared to electromagnetism or the nuclear force, it's weak.
A small magnet can lift a paperclip against the entire gravitational pull of Earth. But what gravity lacks in strength, it makes up for in range. It never switches off, it never locks in, and it acts on everything with mass.
This quiet persistence is what makes it such an effective organizer. Without gravity, Earth wouldn't be round. It wouldn't even be a planet. The matter that formed Earth would still drift in a loose cloud, never compacting into anything solid.
Planets form because gravity pulls on dust and gas over time, compacting them more and more until pressure and heat force the material into a dense spherical shape.
The same force pulled the core, mantle, and crust together.
not as random layers, but in an order reflecting their density. Heavy elements like iron and nickel sank toward the center. Lighter materials floated to the top.
Gravity sorted the planet by weight, and this sorting still determines how Earth functions. But gravity does more than just shape Earth itself. It also holds the moon in orbit, pulls on the oceans to create the tides, and keeps Earth on a stable path around the sun.
Without it, the planet wouldn't just lose shape. It would lose everything that holds it together. No orbit, no seasons, no protection from the harsh vacuum of space. Orbit, in particular, is worth stopping at. Earth's path around the sun isn't random.
It follows a stable, nearly circular path. This orbit doesn't happen automatically. It's the result of balanced forces, Earth's forward motion and the inward pull of the sun's gravity. Too fast, and the planet would fly off into space.
Too slow, and it would spiral inward. But Earth's speed and position work together to hold it in a near-perfect loop, a kind of tumble that never ends. This stability makes long-term climate models possible.
It also provides a predictable basis for seasons, day length, and solar energy. Life adapts to cycles, and these cycles depend on gravity doing exactly what it does. It's not just the sun that pulls on Earth.
The moon's gravity creates bulges in the oceans that we experience as tides. The solid Earth even shifts slightly in response, an effect called tideous. These tiny movements contribute to stress within the crust, which, over long periods, influences tectonic activity.
In other words, gravity doesn't just hold things together, it shapes how they move and evolve. Even the tilt of the Earth's axis, the angle that gives us seasons, is held stable in part by gravitational interactions.
Without this stabilization, the planet might tilt more over time or rotate erratically. Instead, the gravity of the sun and moon keeps the tilt within a narrow range.
This is another way gravity maintains a predictable environment, not by fixing everything in place, but by creating boundaries within which change can occur. On a smaller scale, gravity influences everything from mountain ranges to river flows.
It pulls glaciers down slopes, channels rainwater into catchments, and shapes erosion over time. The landscapes we see, valleys, cliffs, plains, are the result of the slow movement of material under the influence of gravity. Even the way trees grow is shaped by gravity.
Roots grow downward. Stems reach upward, guided by tiny cellular mechanisms that sense the pull of gravity. All these effects are easy to miss because they happen slowly. Gravity makes no sound.
It doesn't flicker or glow, but its influence is constant, and it connects every part of Earth's systems from the rotation of the core to the position of clouds in the sky. Beyond that, there's the human aspect.
Our own biology is tuned to Earth's gravity. The strength of our bones, the way our blood circulates, even how we maintain our balance when we stand, all depend on a specific gravitational force. In low gravity, muscles weaken, fluids shift, and vision can deteriorate.
This is why astronauts experience a whole host of changes in space. Their bodies are adapted to a specific force, 9.8 meters per second squared. And without it, everything must readjust. If Earth had a slightly larger mass, gravity would be stronger. Objects might need to be shorter or more robust. If gravity were weaker, the atmosphere might be thinner. It might even evaporate over time. So the size and mass of a planet aren't just abstract numbers.
They are part of the conditions that make life on the surface possible. The atmosphere remains in place. Water flows as it does. Humans and animals grow to specific sizes. Even birds and insects fly with wings that evolve for these specific conditions.
And beyond Earth, gravity still acts as the master architect. It holds galaxies together, shapes the motion of stars, and bends the light from distant objects. It's something we've measured and used to detect things we can't even see directly.
This bending of light, called gravitational lensing, is one way we know dark matter exists. We can't see it, but we do see its effects.
Just as we can't see gravity, but we feel its presence in everything that stands still or moves in a particular direction. In a universe where so much seems chaotic or random, gravity is one of the few things that brings order.
Not in a perfectly mechanical way, but in a quiet, steady way. It doesn't explain everything, but it provides the conditions under which other things can happen. And without it, none of this would be here.
Of all the substances existing in the universe, water may seem like one of the simplest. 2 hydrogen atoms, 1 oxygen atom. That's all it takes. And yet, it behaves in ways that make it much more than just a chemical compound.
On Earth, water is everywhere. It fills the oceans, shapes the weather, carves the landscape, and flows through every living cell. It is essential for life as we know it.
But when you start looking at how it behaves and how rare this behavior is, it becomes harder to think of water as a simple fluke. Water has a number of properties that make it unusual.
One of the most important is its ability to exist in all 3 states, solid, liquid, and gas, across the range of temperatures found naturally on Earth. This is not a common occurrence.
Most substances tend to prefer one state or require extreme conditions to change, but water can freeze, melt, and evaporate within a narrow range that neatly matches the planet's climate.
This alone may not seem all that remarkable until you consider what these phase transitions actually do. When water evaporates, it absorbs heat, helping to cool surfaces. When it condenses into clouds, it releases this heat, warming the atmosphere.
This process plays a vital role in distributing energy across the globe. It drives weather systems, helps regulate temperatures, and keeps the climate from tilting too far in any one direction. Another key property is water's high specific heat capacity.
This means it can absorb a lot of energy before its temperature begins to change. This turns oceans and lakes into thermal buffers. They absorb heat in the summer and release it in the winter, smoothing out temperature fluctuations that would otherwise be much more extreme.
Without this buffering, the difference between night and day, or summer and winter, would be much more significant. But perhaps water's most well-known property is that it expands when it freezes. Most substances become denser as they cool.
Water does too, up to about 4 degrees Celsius. Then, as it approaches freezing, it begins to expand. The result is that ice floats. This single feature has enormous consequences.
It means lakes and oceans freeze from the top down, creating an insulating layer that protects the water below. Life continues beneath the ice. Ecosystems survive the winter, and when the ice melts, it doesn't sink and destroy everything below.
Then there's how water behaves as a solvent. Water, sometimes called the universal solvent, has the unique ability to dissolve more substances than any other liquid, allowing it to transport minerals, nutrients, and gases through soil, rivers, and living systems.
Within the body, water transports substances in and out of cells, carries hormones, regulates temperature, and maintains structure. Its polarity, caused by the presence of a slightly positive and slightly negative side, allows it to form hydrogen bonds,
which in turn influence how proteins fold, how DNA maintains its shape, and how enzymes function.
These characteristics are not random. They arise from the angle of the H2O molecule, the way the electrons are distributed, and the nature of the bonds involved.
Even the slightest change in these details causes water to behave differently, perhaps less flexibly and less hospitable to life. However, here on Earth, water does exactly what it needs to. What's more interesting is that water is quite common in the universe.
Hydrogen and oxygen are both abundant elements. We found evidence of water in many places, as ice on moons and asteroids, vapor in comets, and possibly as liquid beneath the surfaces of some planets or moons.
But what Earth has, and what's much rarer, is water in large, stable quantities on the surface. Oceans cover about 70% of the Earth's surface. That's a huge amount, and they've been around for billions of years.
No other planet in the solar system has anything like it. Mars has ice and may have once held liquid water, but it has long since vanished from its surface. Venus may also have once had oceans, but its atmosphere changed and evaporated them. The fact that Earth's water has persisted without completely freezing or evaporating means the planet remained within a narrow temperature range for a very long time. How Earth acquired all this water remains a subject of debate. One theory is that the water was locked in the minerals from which the planet formed and was slowly released over time. Another theory holds that it arrived later, delivered by icy comets or asteroids. Perhaps it's a combination of both.
But in any case, the quantity and distribution of water was just right to create oceans, maintain weather, and support the hydrological cycle, evaporation, condensation, precipitation, and runoff, which constantly moves between land, sky, and sea. This cycle supports ecosystems of all kinds. It nourishes forests, fills rivers, forms coastlines, and erodes mountains. It transforms rocks into soil and transports nutrients from one place to another. Without it, Earth would not be the green, fluid, and vibrant planet we know. The Earth would dry out. Plants would die.
Food chains would collapse. Water is more than just an ingredient for life. It is the system through which life moves. Even its interaction with light plays a role.
Water is transparent in the visible spectrum, allowing sunlight to penetrate the oceans and fuel photosynthesis in aquatic plants. If it were opaque, underwater ecosystems would have to survive in the dark. But this doesn't happen because water transmits light, but only a little.
It filters out harmful ultraviolet rays while still providing enough energy for life to thrive. Rain, snow, clouds, fog, all are part of the constant movement of water. They influence temperature, visibility, behavior, and even mood.
They change how animals migrate, how people plant crops, how landscapes develop, and the timing of these patterns, how often it rains, how long snow lasts, when dry seasons begin, is linked to everything from geography to air currents in the planet's tilt.
Earth's climate and its aquatic systems are locked in a feedback loop that currently supports a wide range of life forms. Even in the deep ocean, far from sunlight, life continues. Hydrothermal vents release heat and minerals, and entire ecosystems cluster around them.
Bacteria convert chemical energy into food, supporting fish, crustaceans, and strange organisms found nowhere else. These underwater environments are a reminder that life doesn't always require light, but it does require water.
There's something striking about the fact that the most abundant liquid on Earth is also the most vital, that a substance so simple in structure is so complex in function.
And that the conditions necessary to support its flow, atmospheric pressure, surface temperature, planetary mass, are intimately interrelated. This doesn't mean water was designed to behave this way. Perhaps life has simply adapted to what water already does.
But even this explanation leaves open the question of why water does all this at all. Why would a molecule made of 3 atoms become the basis for a system that supports such a vast and diverse network of life in another universe with different physics?
Water might not exist, or it might behave differently, or it might be irrelevant, replaced by some other medium. But in this universe, with these rules, and on this planet, water is almost perfectly suited to this role. It flows, transports, dissolves, freezes, and reforms, quietly orchestrating the background processes on which life depends every minute. When you begin to look closely at the forms life takes, the way trees branch, shells twist, petals align, or crystals form, you begin to see patterns, not just similarities, but repetition.
Certain structures appear again and again across different scales and environments. Some are symmetrical, some spiral, some correspond to relationships that can be described by prime numbers. And while all of these forms can be explained by physical processes, consistency is hard to ignore.
Symmetry is perhaps the easiest to spot. It appears in faces, bodies, leaves, insects, snowflakes. When both sides of something mirror each other, whether vertically, horizontally, or rotationally, we call it symmetry. Such balance can be structural, helping an organism move more efficiently or distribute weight evenly. But symmetry also appears to be perceptually attractive. The human brain is hardwired for rapid recognition. We tend to find symmetrical faces more attractive.
We use symmetry in design, architecture, and symbols. It feels ordered, familiar, and complete. In nature, symmetry often serves a purpose. Butterfly wings match because they form together. Starfish have radial symmetry, which helps them move and respond to their environment.
Leaves grow in pairs to capture light evenly. Even many viruses are built with symmetrical protein shells, not because they're supposed to be pretty, but because symmetry is efficient. It allows the same genetic instructions to be reused. From a material standpoint, it's a shortcut.
Make one part, then copy it over and over again. But not everything is reflected. Some of the most interesting structures in nature are spirals. You see spirals in snail shells, hurricanes, whirlpools, and galaxies.
You see them in pine cones and sunflower caps, in fingerprints and animal horns. Spirals often appear where growth occurs. They allow structures to expand outward while remaining compact.
As an organism adds material, a new scale, a new layer, a new petal, the spiral makes room without disrupting the whole. Many of these spirals follow a mathematical pattern called the Fibonacci sequence.
It's a series of numbers where each new number is the sum of the previous two. 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence is evident in the arrangement of petals, the branching of trees, the packaging of seeds.
The relationship between Fibonacci numbers approximates what's known as the golden ratio, a proportion that appears to repeat itself in both nature and art. It's not universal, but it's common enough to attract attention. These patterns don't require intelligence to emerge.
They can arise naturally through growth and competition. For example, if a plant grows new leaves and tries to minimize how much each one blocks sunlight from others, it may develop a spiral arrangement.
This arrangement, in turn, aligns with the golden angle, the fraction of the full rotation that distributes elements efficiently. No one designed it to be beautiful. It just works, and yet ultimately proves beautiful in every case.
This is where the idea of sacred geometry often arises. It's a term that has been used in various ways, sometimes spiritual, sometimes symbolic, sometimes simply poetic, to describe patterns that seem to carry meaning because of their structure: circles, triangles, spirals, hexagons. These forms appear in religious art, ancient architecture, mandalas, and monuments. But they also appear in snowflakes, honeycombs, and coral reefs. The overlap between natural geometry and human expression is no coincidence. Perhaps we copy what we see.
We repeat these forms in our buildings and symbols because they are already familiar to us from the natural world. Perhaps we are wired to notice them, to feel that certain forms are more complete, more meaningful, more pleasing, because they follow simple rules that we can sense, even if we don't consciously understand them.
Hexagons are a good example. Bees build their hives using them because it's the most efficient way to divide a surface into equal sections with a minimum amount of material. This creates a strong, stable structure using the least amount of wax.
But you also see hexagons in basalt rock formations, like the Giant's Causeway, or in the bubbles that settle into foam. The same form emerges from pressure and physics, even when bees aren't involved. Crystals are a different matter.
Their atoms arrange themselves in repeating patterns that can form cubes, prisms, or even complex branching shapes. These shapes aren't cut or placed because that's how they grow. The structure emerges from the internal rules of how molecules interact.
Temperature, pressure, and chemical bonds direct growth, resulting in something that looks both random and deliberate. You also see fractals, patterns that repeat at different scales. Tree branches split into smaller branches. Rivers divide into tributaries. Lightning forks. Veins diverge. Lungs divide.
Each level appears as a smaller version of the whole. Fractals are efficient ways to distribute energy or resources. They allow a system to reach many points from a central core, and they often emerge from simple rules applied repeatedly.
This is what makes many of these patterns compelling. They don't require complexity to emerge. They emerge from feedback loops, constraints, and repeated processes. They're built into the way materials behave under certain conditions. But even if they're not the result of intention, they appear intentional. They create a kind of visual logic, something that seems too consistent to be meaningless. There's also a sense of harmony in the way these patterns fit together.
The way branches fill space without overlapping. The way spirals pack seeds without gaps. The way snowflakes grow along symmetrical paths. These aren't chaotic results. They're structured.
And when you accumulate enough structured results, you begin to wonder if the structure itself isn't part of a deeper picture. Some scientists have suggested that certain shapes, such as spheres, spirals, or hexagons, are preferred solutions in physical systems.
That is, given enough time and freedom, matter will gravitate toward these shapes because they're stable or efficient. This is a useful explanation, but it still raises the question, why are stable, efficient solutions also the ones we find everywhere? Why do they support life?
Why do they appear in both cells and stars? There's no need to assume anything mystical to notice patterns, but it's worth asking why the rules of the universe produce results that seem both functional and aesthetically consistent. Why do the forms that help plants grow also manifest themselves in our sense of art and beauty? Why are the most effective structures also the most common? This doesn't imply a blueprint in the strictest sense.
No written plan, no design document, but it can offer a framework, a set of principles that define what is possible, what is probable, and what is sustainable.
Whether this framework derives from physics, mathematics, or something more abstract, it is clearly embedded in the way matter organizes itself, and it's part of what makes the living world so interconnected.
Looking at the outer forms of life, it's easy to be impressed by how well everything seems to fit together. But when you step inside a cell, into the nucleus, into the molecules that govern everything, this sense of coherence doesn't disappear.
If anything, it's becoming more acute. The internal systems of biology are precise, multi-layered, and full of interconnected parts. They don't just function, they coordinate. And the deeper you dive, the more this begins to seem like more than just chemistry.
At the heart of it all is DNA, deoxyribonucleic acid, the molecule that stores genetic information. Every known living thing uses DNA, or its close relative RNA, to store instructions on how to build and maintain itself. DNA isn't just a substance, it's a code.
It's constructed from 4 types of molecules: adenine, thymine, cytosine, and guanine, arranged in sequences that determine how proteins are made. These proteins, in turn, control the machinery of life.
The genome is often compared to a language, not only because of its limited symbol set, but also because of its structure, syntax, and meaning. A slight change in the nucleotide sequence of deoxyribonucleic acid can alter the configuration and functionality of a protein.
Sometimes this happens subtly, and sometimes dramatically. The same gene can be activated in different organisms, performing similar functions with slight variations. Moreover, the mechanism of reading, copying, and interpreting information is so orderly that it resembles a purposeful process rather than a chemical reaction.
Studying the principles of deoxyribonucleic acid, it becomes clear that its role is not limited to simply storing information. It also controls it. There are sections of the sequence that act as start and end markers, signaling the moment of gene activation.
There are also regulatory genes that control the activity of other genes. Along with this, there are error correction systems that scan deoxyribonucleic acid during the copying process and eliminate inaccuracies.
And all these processes occur within a structure no larger than a few micrometers in size, in every cell of every living organism. This level of organization raises questions not so much because of the difficulty of understanding the process of its origin, but because of the impossibility of ignoring its effectiveness.
The generally accepted explanation is evolution through natural selection. Subtle changes in genetic material give rise to variations. Variations that favor survival are passed down from generation to generation. This leads to complexity, and the evidence for this process is numerous and compelling. We can observe it in fossils, in laboratory experiments, in the shared genetic traits of related species. However, even within this framework, the mechanisms themselves are astonishing in their complexity. Proteins fold into specific three-dimensional structures based on the interactions of their amino acids.
This folding process is crucial for their functionality. A misfolded protein is often unable to perform its function. Yet inside living cells, this folding process occurs automatically, guided by the sequence of amino acids and with the help of other molecules that act as guides.
There is no conscious intention behind all this, yet the system functions with an undeniable elegance. This is not a random series of trials and errors.
It is thousands of interconnected elements working in concert, in the right sequence, at the right time.
Let's consider enzymes, proteins that significantly speed up chemical reactions. Without them, most of the reactions that sustain life would be too slow to be of any significance. However, thanks to them, these reactions occur millions of times faster. Enzymes are highly specific.
Each one fits its purpose like a key to a lock. They are not just functional, they are selective. And life depends on this selectivity to control when and how various processes occur.
Then there are molecular motors, miniature devices made of protein that move various substances within cells. Some move through cellular structures, transporting cargo from one place to another. Others rotate, pump, or open and close channels.
They convert chemical energy into motion, often resembling mechanical devices, but on a much larger scale. None of these systems is unique to complex life. Bacteria and plants have them. Every living organism is built using variations of the same tools.
The details may differ, but the basic principles remain the same. This consistency points to a common origin, confirming the theory of evolution. However, it also raises the question of the source of the original instructions, the first sequences, the first proteins, the first membranes.
Abiogenesis, emergence of life from non-living matter, is an area of active scientific research. Scientists have proposed various models for how the first self-replicating molecules might have formed in the conditions of early Earth.
Some theories involve clayey surfaces, deep-sea hydrothermal vents, or ice-covered lakes. Despite progress, no explanation has gained universal acceptance. The difficulty is that life requires more than just molecules. It requires systems that replicate, regulate, respond, and evolve.
And while it is possible that these systems gradually emerged from simpler forms, the transition between chemistry and biology remains one of the most challenging stages to model. This gap, this chasm between random molecules and functioning cells leads some to wonder whether biology exhibits signs of engineering design. Not necessarily in the sense that machines are designed by humans, but in the sense that the components seem unusually well adapted to the roles they play.
Code is not just data. This is executable code. It carries out instructions, modifies itself, and adapts in real time. Even the way genetic information is packaged within the nucleus testifies to this efficiency.
Human deoxyribonucleic acid, if stretched out, would be about 2 meters long, yet it fits into a microscopic space, enveloped in proteins, coiled into loops, and organized so that the right genes can be accessed when needed. This is not chaos. This is control.
And beyond DNA, cells contain multiple layers of feedback systems, signals that trigger growth, division, repair, or death. These systems maintain the equilibrium of organisms. They respond to damage, stress, hunger, infection. They communicate with each other through chemical messages, adjusting them depending on conditions.
It's not that errors don't happen. They do. But the system doesn't depend on perfection. It depends on resilience. Biology is not flawless. Mutations can cause disease. Systems break down.
But the fact that life continues despite constant disruption is itself a kind of engineering, not rigid, but adaptive, not static, but dynamic. This doesn't mean that cells were designed by a conscious mind, It's entirely possible that the systems we see have survived because they work, and that's entirely plausible. But when you consider the level of coordination, the natural comparison isn't just a factory, a city, or a machine, but a code base. A set of instructions that not only builds itself, but also maintains and updates itself.
And just like software, biology has layers. There's the raw code, the DNA sequence. There's the operating system, the cellular machinery that interprets it. There are inputs and outputs, error correction, feedback loops, and there are networks, interactions between genes, proteins, cells, and organs that create behavior, reactions, even thoughts.
So the question shifts. Perhaps the question isn't whether biology was designed, but whether engineering and biology can be viewed in the same terms. Is the comparison merely metaphorical?
Or does the structure of life suggest a deeper connection between systems that emerge through evolution and those that are intentionally constructed? This question remains open, but the deeper we delve into the code of life, the more structured it appears.
Not random, not improvised, but multi-layered, regulated, and deeply integrated. Once you understand that DNA acts as a code, it becomes difficult not to think of it as a kind of language.
It doesn't use words or grammar the way spoken languages do, but it has its own rules, its own alphabet, syntax, structure, and meaning. It's written in a 4-letter chemical script and contains instructions not only for building proteins, but also for when, where, and how those proteins should be produced.
It's information stored physically, instructions embedded in matter. The question is whether this language was invented, discovered, or something in between. DNA isn't just a long chain of chemicals. It's organized into genes, which are sequences that can be transcribed and translated into proteins. But these genes are only part of the story. They are also regulatory regions, sequences that tell the cell when to start and stop reading a gene, how much protein to produce, or what conditions should trigger a change.
There are enhancers and silencers, sequences that influence genes from a distance. There are introns, which are parts of a gene that are cut out before the final product is produced.
And there are non-coding regions, sometimes called junk DNA, though this term is gradually disappearing, which may play a role in structuring the genome or influencing how it is expressed.
All of this behaves less like raw code and more like a programming language, which includes not only instructions, but also a context that supports layered and conditional behavior. In computers, code is compiled and executed. In cells, DNA is transcribed and translated. Both processes require a system that knows how to interpret a set of symbols. Both rely on precision, structure, and timing. And both can break down when rules are not followed. But DNA doesn't sit there to be read all at once. Only a small portion of it is active at any given time. Different genes are turned on in different cell types at different stages of development in response to different signals.
The same DNA sequence can produce very different results depending on where it resides in the body or what environmental conditions are present. This flexibility is part of what makes complex life possible, and is part of what makes DNA seem like more than just data. It behaves like a system. What's interesting is that this system appears to be universal. All known life on Earth uses the same basic genetic code.
4 identical letters, a similar codon structure, the same translation rules. A codon is a set of 3 bases encoding a single amino acid. There are 64 possible codons, but only 20 standard amino acids. Consequently, the system is redundant. Some codons are synonymous.
Others function as punctuation marks, indicating the beginning and end of a sequence. However, this system is common to bacteria, plants, animals, to all living things.
This points to a common origin, to a moment in the distant past when life settled on a single code, and each branch of evolution carried it forward. But this also raises the question, why this particular code? Why this particular structure?
Scientists have investigated whether the genetic code is optimized, whether it represents the best possible arrangement of codons to minimize errors and maintain flexibility. Some studies suggest that it is close to optimal, not perfect, but surprisingly effective in mitigating the effects of mutations and ensuring robustness. If this is true, then perhaps life has adopted not just any code, but one that works particularly well. Whether this means that the code was naturally selected or that certain structures are more likely to survive depends on how you look at it.
In any case, what we have now is a system that works in all forms of life and continues to work, with variations, for billions of years. There is also the question of interpretation.
Humans did not invent DNA, but we discovered how to read it, how to translate chemical sequences into information. And when we did, we found something astounding. Not just complexity, but logic. Not just molecules, but instructions.
This discovery led to the emergence of entire fields of research: genetics, molecular biology, bioinformatics. We now manipulate DNA with tools like CRISPRs, redesigning genes with increasing precision. We can synthesize sequences, insert them into cells, and observe their function.
In a sense, we began to write the language of life. But we didn't create the language itself. It was already there. This is where the idea of design often comes back into the conversation.
Not because DNA looks manufactured like a computer chip, but because it behaves purposefully. It processes information in ways that resemble software, logic circuits, or carefully planned instructions. It is not random noise.
It is a structure with an output, and it is built into every living thing. There's also the question of meaning. In human languages, meaning comes from intention. Someone writes or speaks with the intent to convey something.
In the case of DNA, meaning isn't conscious, it's functional. A sequence has meaning because it causes something. It builds a protein, triggers a reaction, allows a process to unfold. But does that meaning carry the same weight?
Is there enough functional significance to call it language, or is it simply a metaphor we borrow from human systems? This is part of what makes this field so ambiguous.
Metaphors work because the systems are similar, but the interpretation depends on what you're looking for. You can view DNA as the result of evolutionary trial and error, where sequences that work are preserved and refined.
Or you can view it as a system so finely tuned that it suggests not necessarily a conscious designer, but perhaps a deeper structure underlying how life organizes itself.
There are even attempts to engineer entirely new genetic codes, alternative base pairs, synthetic amino acids, new translation rules. While these experiments show that other systems could work in theory, this only underscores how remarkable the natural system is.
It's efficient, it's resilient, and it supports a vast array of biological outcomes, all built on the same basic script. The question of whether DNA was discovered or designed may come down to what you mean by those words.
It wasn't designed by humans, nor was it discovered in the sense that mathematics or physics might be something eternal and abstract. It's a structure that seemingly emerges naturally from the rules of chemistry and evolutionary dynamics.
But the fact that it works so well and so consistently
makes it feel like it possesses properties we typically associate with engineered systems. This doesn't prove anything, but it shifts the conversation from thinking about how life began to noting that life behaves as if it were built on a kind of deep grammar that we didn't invent and that we're still learning to read.
Living things cannot survive without a protective barrier, not only physically, but also chemically. The news editorial team presents the outer shell separating the interior from the exterior. At the cellular level, this is the cell wall. At the planetary scale, it is the atmosphere.
However, unlike the walls of a container, the Earth's atmosphere is not static. It changes, moves, reacts, and regulates. It is not alive in itself, but acts as part of a living system. It holds everything in, but also releases only as much as needed.
The atmosphere consists primarily of nitrogen, about 78%, followed by oxygen, argon, carbon dioxide, and trace gases. This mixture may seem normal, but it is anything but. Change the ratio slightly, and the system stops working. Too much oxygen and forest fires become uncontrollable.
Too little, and animals suffocate. Without nitrogen, plants cannot grow. Without carbon dioxide, photosynthesis ceases. The percentages are not symbolic, they are functional. They maintain the chemistry on which life depends. Balance did not arise overnight.
Early Earth had a different atmosphere, full of volcanic gases such as methane, carbon dioxide, and sulfur compounds. It was toxic by modern standards, but not sterile. Microorganisms evolved in it, and eventually, some began producing oxygen through photosynthesis.
This oxygen reacted with iron in the oceans, forming rust, which sank to the sea floor. Oxygen levels remain low for a long time. Then they began to rise slowly, then rapidly. This change, called the Great Oxidation Event, transformed the atmosphere.
Oxygen allowed for more efficient energy production within cells. This made multicellular life possible, but it also caused extinction. Organisms adapted to the old atmosphere could not survive in the new one, so the system rebooted.
Life evolved again according to new rules and new strategies. Oxygen didn't just provide complexity, it anchored it. Even today, oxygen levels are regulated not by a machine, but by feedback between ecosystems, geology, and climate. Plants and algae produce it, animals consume it.
Fires reduce it. Weathering rocks locks up carbon. Volcanoes release it. If one part shifts too far in one direction, others adjust. The result is not perfect stability, but limited variability. It's a system that breathes, cycles, impulses, and feedback.
One of the most noticeable aspects of the atmosphere is its pressure. At sea level, it presses down with a force of about 14.7 pounds per square inch.
This pressure keeps water liquid, ensures efficient gas exchange in the lungs, and maintains everything from the boiling point of liquids to the structural strength of biological tissues. If it were much lower, water would evaporate too easily.
If it were higher, breathing might not work as well as it once did. Pressure maintains conditions conducive to life, and life, in turn, maintains the gases that maintain pressure. The composition of the atmosphere also determines how heat moves around the planet.
Some gases absorb and emit infrared energy. These are the greenhouse gases: carbon dioxide, methane, water vapor, and others. Without them, Earth would be cold and lifeless. But if there are too many of them,
the planet will overheat. The system is dynamic.
Greenhouse gases come and go, but the range remains largely within the limits where life can adapt. Next comes the ozone layer, a thin layer of the atmosphere that absorbs most of the sun's ultraviolet radiation. Ultraviolet light is harmful to DNA.
Without this protection, mutations increase, cells die, and life becomes unstable. But with sufficient ozone, harmful rays are blocked and beneficial light passes through. The ozone layer forms naturally through reactions involving oxygen and sunlight, but it can also be damaged by artificial chemicals.
This vulnerability is not a flaw. It's a sign that the system is sensitive, tuned to specific interactions based on a constant supply of energy and chemicals. The atmosphere also moves. Winds distribute heat, moisture, and particles across the globe. Jet streams drive weather patterns.
Ocean currents interact with air currents. Together, they move energy from the equator to the poles, equalizing temperatures and shaping climate zones. Without this movement, the tropics would overheat and the poles would freeze completely.
With it, the planet remains habitable across a wide range of latitudes. Then comes the hydrological cycle, driven by evaporation, condensation, and precipitation. Water vapor rises, forms clouds, and then falls as rain or snow. This rain feeds rivers, replenishes aquifers, and grows forests.
The atmosphere is the vehicle for this movement. The atmosphere connects land, sea, and sky, and not in a poetic sense, but in a chemical one. And it does so without the need for centralized control.
It happens thanks to temperature, pressure, altitude, sunlight, and physics, not planning. But the result looks like coordination. Atmospheric circulation also transports tiny particles, dust, pollen, and microbes. Some of these particles influence cloud formation. Some carry nutrients across the oceans.
Some seed ecosystems in entirely new places. These aren't just side effects, they're transport mechanisms. They allow the biosphere to move, adapt, and evolve. And through it all, the atmosphere remains dense enough to matter.
It extends about 100 kilometers upward, but most of its mass is within the first 10 to 15 kilometers. This narrow layer contains everything we breathe, every cloud we see, every sound we hear. Beyond it, space begins.
There's no sharp boundary, just a slow thinning until nothing remains. This thinness makes it fragile, but it also makes it functional. It lets sunlight through. It allows heat to escape. It holds just enough. This thin shell also makes flight possible.
Birds, insects, airplanes all rely on air pressure and lift. Even seeds and spores move through the air. The atmosphere is more than just a shield. It is a medium, a space where movement occurs.
And yet, despite all this, the atmosphere doesn't draw attention to itself. It's easy to forget that every breath you take is the product of planetary systems, that the oxygen in your lungs may have come from an Amazonian tree or an ocean microbe.
That the air around you isn't just empty space, but the result of billions of years of feedback, adaptation, chemistry, and movement. It's not that the atmosphere is conscious, but its behavior suggests structure, not random drift, but cycles, not stasis, but equilibrium.
This kind of regulation hints at a system with limits, thresholds, and memory. Even if the materials are right, even if the chemistry works, time still matters. Not just in seconds or hours, but on vast scales, seasons, cycles, and eons.
On Earth, things don't just happen. They happen at intervals, in rhythms. Some quickly, some slowly, some measured by the slow tick of geological time. There's nothing mechanical about these cycles, but they act like clocks, not constructed, but real.
And it's this timing that keeps everything functioning. The Earth rotates once every 24 hours. This rotation gives us day and night. It sets the pace for sleep, activity, photosynthesis.
Every living thing, from insects to trees to humans, has internal mechanisms that synchronize to this pattern. Circadian rhythms, hormonal cycles, the timing of flowering and feeding. These are not simply responses to light. They are programmed, shaped by millions of years of repetition. The planet rotates, and life rotates with it. The year is fixed. One revolution around the sun takes about 365.25 days. This motion, combined with the planet's axial tilt, creates seasons. These seasons are more than just cosmetic.
They shape migrations, initiate reproductive cycles, and regulate growth. Bears hibernate, birds migrate, crops ripen. Even microorganisms time their behavior to seasonal cues. Such coordination would be impossible without consistent orbital timing, and the orbit itself is remarkably stable.
Earth's path around the Sun is nearly circular, with enough eccentricity to cause variations in solar energy without causing extremes. Some planets have more elliptical orbits, resulting in hotter summers and colder winters.
Earth's nearly constant distance from the Sun maintains solar energy within a range that supports life year-round, even with seasonal variations. But a planet's motion involves more than just rotation and orbit.
There's precession, a slow wobble of the axis like a spinning top that takes about 26,000 years. There's also a change in the tilt of the axis itself and changes in the eccentricity of the orbit over time.
These cycles, known as Milankovitch cycles, influence long-term climate patterns, ice ages, glacier advances, changes in precipitation, all tied to these deeper rhythms. Time isn't perfect, it's probabilistic, but regular enough to shape history. Even the moon plays a role.
Its orbit influences the tides, of course, but also the length of the day. Over billions of years, the moon's gravitational pull has slowed the Earth's rotation. Days are getting longer by a few milliseconds per century. It's slow, but it adds up.
A billion years ago, days were closer to 18 hours. This has biological implications. The alternation of day and night influences the duration of photosynthesis in organisms, the synchronization of internal clocks, and the processes of heat accumulation and dissipation.
Evolution did not occur within a fixed framework, but adapted to constantly changing conditions. Other cyclical processes occur in parallel. For example, solar activity follows an 11-year cycle with peaks and troughs in sunspot numbers and solar radiation levels.
This activity influences the Earth's magnetic field, affects the operation of satellite systems, and may play a role in minor climate changes. Geological cycles unfold over tens or hundreds of millions of years, involving the movement of tectonic plates, the opening and closing of ocean basins, and the rise and fall of mountain ranges.
Even mass extinctions exhibit a certain periodicity, although the causes of this phenomenon are still a subject of debate. Biology itself is also a cyclical process.
Within each cell, a molecular clock operates continuously. measuring time using proteins whose levels rise and fall in repeating cycles. These cycles are not simply reactions, but mechanisms that allow the cell to anticipate future events.
Cells don't simply react to light, they anticipate its presence. Genes are switched on and off at specific times of day. Repair systems are activated when damage is most likely. Organisms' behavior is not simply reactive, it follows a specific time schedule.
In humans, an internal clock regulates sleep, body temperature, hormone production, and digestion. A disruption of this internal clock relative to external conditions leads to jet lag. Disruption of these rhythms can lead to health problems. The body requires not rigid fixation, but pattern.
And this pattern stems from the movement of the earth. Even reproductive processes are subject to cycles. Menstrual periods, pregnancy, mating seasons, all are directly or indirectly linked to light and time.
Some of these connections are obvious, while others are rooted in distant evolutionary history and shaped by ancient mechanisms that no longer serve obvious functions, but continue to operate in the background. Cultural time also exists outside of biology.
Humanity has created calendars to track the movements of the sun and moon. Agricultural systems depend on the timely planting and harvesting of crops. Religious rituals are timed to coincide with solstices, equinoxes, and phases of the moon.
Our entire system of measuring time, including seconds, hours, and years, is built on the motions of the earth. We wear watches on our wrists, but they're only miniature versions of cosmic rhythms. None of this implies any control over these processes.
The earth is unaware of its rotation. The sun does not track its position. The moon does not calculate the tides. Yet the results of these processes manifest as pattern, repetition, and rhythm.
This occurs not because someone decreed it, but because it persisted long enough for life to notice. And once life noticed, it integrated these rhythms into itself. What is remarkable is how these rhythms overlap.
Rapid cycles like day and night build on slower ones like seasons, years, and orbital changes, which in turn build on even deeper cycles. Continents shift, mountain ranges rise, and stars age. Each layer influences those above it.
Together, they form a kind of framework, not imposed from the outside, but rather emerging from interaction, movement, and inertia. This framework creates windows of opportunity, times when certain conditions such as warmth, light, moisture, and stability converge and new life forms emerge. At other times, it creates pressure, ice, drought, competition, change. Life adapts to both of these scenarios, but it takes time to do so. And Earth's regularity gives it that time. There's a difference between predictability and purposefulness.
The fact that a clock tells time doesn't mean someone has to keep track of it, but it does mean it can be relied upon. It turns out that Earth can be built. Life, weather, chemistry, culture, all of it layered onto a consistent timeline.
And none of it will work if the tempo is disrupted too much. There are aspects of biology that seem to have evolved gradually, step by step. They can be traced. Small changes, marginal advantages, slow shifts over generations.
But there are also features that seem to leap forward, not because they cannot be explained, but because they work so well it's hard to imagine how they could work partially at all. The human eye is one such example.
It is often cited as an example of complexity. a system with many parts, each dependent on the others. Light enters through the transparent cornea. The iris regulates brightness. The lens focuses the image. The retina converts photons into electrical signals.
These signals are transmitted along the optic nerve to the brain, where an image is formed, not passively received, but actively interpreted. Every second, the eyes take in millions of inputs and sort them by movement.
Color, contrast, distance, threat, comfort. All these aspects of perceiving the world are continuously processed by our senses. What makes this process even more fascinating is that the eye is not just a light sensor, but a complex dynamic optical system.
The lens changes shape to provide clear vision at both near and far distances. Pupils dilate or constrict in response to both light intensity and a person's emotional state. Tiny muscles track moving objects, stabilize the visual field, and coordinate with head and body movements.
The eye does not function in isolation. It is embedded in a system of coordination and prediction. And it's not just about hardware. The brain adds layers of processing, detecting object boundaries, adjusting colors, and recognizing patterns.
It fills in blind spots and stabilizes the view of the world, even when the head is moving. The brain interprets what it sees based on memory, expectations, and context. Vision is an interaction, not a direct recording of reality.
The traditional explanation for this phenomenon is evolutionary. Eyes evolved from light-sensitive areas on the bodies of ancient organisms. Over time, these areas deepened, formed lenses, acquired muscles, and refined focusing.
Similar developmental stages can be observed in nature today, from simple photoreceptors in jellyfish to complex compound eyes in insects and the highly developed eyes of vertebrates like ours. Each evolutionary step provided a survival advantage, even if the system was not yet fully formed.
This explanation is supported by scientific research. However, it is remarkable how far the eye has evolved, and not only in humans, but in other animals as well. Birds of prey can see ultraviolet light and detect movement over vast distances.
Some species of shrimp perceive polarized light and distinguish colors we cannot even imagine. Cats and owls can function in near total darkness. Squid eyes, designed differently than ours, like cameras, provide similar functionality.
These are not weak, crude versions of vision, but finely tuned systems that are fast, responsive, and high resolution. And the eye is just one of many examples of amazing sensory systems created by nature.
Echolocation in bats and dolphins involves sending high-frequency sound pulses and interpreting the reflected signals. It's a fully functional three-dimensional mapping system operating in milliseconds underwater or in flight. Electric fish use electric fields to detect objects in turbid water.
Some insects see in the ultraviolet or infrared range. Some snakes sense the heat emanating from warm bodies. These systems don't just detect. They analyze information and operate in real time. They interpret noise as structure.
Even something as mundane as the human hand is an engineering marvel. Numerous bones, tendons, muscles, and nerves work in concert to enable fine movements. The opposable thumb allows for grasping and manipulation of objects.
The fingertips are capable of recognizing textures at the microscopic level. The coordination between vision and touch enables a precision that machines have struggled to match.
Playing a musical instrument, typing on a keyboard, tying a knot. These are not brute force movements, but carefully calibrated, tuned, and constantly adjusted actions. Some parts of the body have the ability to regenerate and repair themselves.
Skin heals, bones fuse, the liver can recover from injury. Other parts of the body, such as neurons, do not regenerate so easily. But even so, the basic design principle remains effective. The brain rewires itself, forming new pathways and compensating for damage.
The system is designed with flexibility, not unlimited but sufficient for survival. Then comes the process of development. Each person begins life as a single cell. This cell divides, differentiates, and organizes into tissues, organs, and systems.
The instructions for this process are written in DNA, but execution occurs in 3 dimensions, continuously and responsively. Cells transmit signals to each other, responding to gradients, concentrations, and contacts.
The body does not simply assemble itself. It grows from the inside out, from simple to complex, constantly checking, correcting, and regulating itself. Certain processes, such as organ formation, system integration, and ongoing changes, are scheduled by the clock.
If the timing is off, development can go awry. But most of the time, this doesn't happen. Development occurs with a precision that rivals engineered systems. This precision doesn't guarantee perfection, but it allows complex systems to emerge reliably.
Similar precision can be observed in less obvious systems. The immune system detects and neutralizes threats, relying on memory and pattern recognition. The endocrine system regulates energy levels, growth, stress response, and reproductive function.
The cardiovascular system delivers oxygen and nutrients with incredible efficiency, regulating blood flow on the fly, responding to movement, temperature, and injury. All of these systems are composed of cells.
Each cell is a compartment with its own internal logistics: membranes, organelles, transport channels, and waste disposal system. The cell functions autonomously, follows instructions, adapts to signals, and constantly repeats this process, dividing, dying, and renewing itself. There's no single trait that proves anything.
And yet, when you combine all the systems together, vision, movement, balance, coordination, communication, what you get is more than just survival. It's ability, awareness, creativity, the ability to interact with the world in a nuanced and sensitive way.
From the outside, humans may appear fragile, soft, slow, tool-dependent. But biologically, the human body is both adaptive and precise. It can run long distances, recover from injury, learn languages, manipulate tools, raise children, coordinate memory with planning, balance emotion with reasoning.
These aren't minor traits. They're fundamental to how humans function. None of this is inconsistent with natural processes. Evolution provides a clear mechanism: variation, selection, adaptation. But even within this system, some traits seem unusually successful, tuned not just to function, but to reign.
The eye doesn't just see. It adapts to light and dark, tracks movement, focuses near and far. The ear doesn't just hear. It discerns tone, direction, rhythm. The body doesn't just move. It climbs, swims, dances, writes. These aren't happy accidents.
They're systems built upon systems, honed over time, interacting at multiple scales. There's no need to call them intentional, but they work so seamlessly that they stand out.
And this leads to a larger question, not just about how individual systems work, but how they work together. The integration, the coordination. What keeps all these processes in sync, and what allows them to respond to an environment that never stops changing?
Some things happen because they're supposed to. Gravity pulls, water flows downhill, metal rusts. These are regular, predictable, mechanical processes. But some events aren't. They're specific, random, and happen only once. An asteroid hits, or a molecule mutates, a volcano erupts.
We call these accidents not because they're mistakes, but because they could have happened differently. They didn't have to happen the way they did. But it's striking how often these accidents produce results that in hindsight seem almost coordinated.
Take the asteroid that hit Earth about 66 million years ago. It fell near what is now the Yucatan Peninsula. The impact released more energy than 1 billion nuclear bombs.
It vaporized rock, triggered global firestorms, darkened the skies, devastated ecosystems, and brought an end to the age of dinosaurs. This wasn't a slow evolutionary process. It was a reset, rapid, brutal, and complete.
But it also freed up ecological space that allowed mammals to expand, diversify, and ultimately dominate. Without this single event, humanity might never have emerged. That's one event. There are others.
About 2.5 billion years ago, Earth's atmosphere began to fill with oxygen, not because of a cataclysm, but because single-celled organisms learned to use sunlight to split water. Photosynthesis. The byproduct was oxygen, which slowly accumulated in the atmosphere and oceans.
At first, it was toxic to existing life, but over time, it enabled the emergence of entirely new forms of metabolism, higher energy output, complex cells, and, ultimately, multicellular life. One biochemical innovation changed the entire trajectory of life on Earth.
Not by design, but by consequence. Around 600 million years ago, multicellular organisms began to evolve more rapidly. Nervous systems, eyes, skeletons. Fossil evidence shows an explosion of diversity in the so-called Cambrian period.
Part of this may have been caused by oxygen levels reaching a certain threshold, part by genetic innovations such as the emergence of regulatory genes that controlled body plans.
Regardless of the cause, time was limited, only a few million years in either direction, and the environment may not have supported such an outcome. Even plate tectonics, the slow drift of continents, shapes outcomes in ways that seem incommensurate with the movement.
The shifting of land masses over millions of years alters ocean currents, isolates species, opens migration routes, and blocks others. It creates mountain ranges that influence rainfall. It brings species together or separates them. And in so doing, it sets the conditions for natural selection.
Who survives? Who mingles? Who goes extinct? The formation of the Moon, most likely the result of a collision with a Mars-sized body, is another example. It was chaotic, high energy, and likely one of the rarest types of impacts.
But the result was a stable moon, which helps regulate Earth's tilt, tides, and rotational stability. Without it, climate patterns might have shifted too much for large ecosystems to hold together. None of these events were guaranteed either.
They were not part of any timetable, but they had consequences far beyond their original scope. Not just chain reactions, but turning points, crossroads where one outcome changed what was even possible afterward. Biology, too, is full of what looked like fortunate coincidences.
the emergence of DNA as a stable information storage system, the development of proteins with flexible functions, the emergence of eukaryotic cells, cells with internal compartments like nuclei and mitochondria. The final step likely came from one cell engulfing another.
Not to consume it, but to work with it. A fusion, an accident that became permanent. This symbiosis allowed for the creation of larger, more complex organisms. Then comes sexual reproduction, which mixes genes and increases diversity, accelerating evolution but requiring cooperation between individuals.
Or the evolution of consciousness, not just behavior, but awareness, memory, planning, reflection. Not inevitable, not universal, but real and connected to a network of preceding events, any one of which could have gone differently.
Even the human brain, with its layers of function, motor control, pattern recognition, language, is built on top of a biological history that began with simple responses to light or touch. Each layer required the work of earlier systems, neurons, then circuits, then coordination between regions.
And at each stage, the conditions had to be just right, and power supply, protection, time to develop. Looking at all this, one way to think of it is as a filter. Many planets can exist.
Many might even have water, heat, or the right chemistry. But to achieve complexity, then consciousness, then civilization, a long list of things must come together. And not just in any order, but in the right sequence, at the right intervals.
Timing must not be wasted. Too early and the system fails. Too late and the opportunity is missed. That doesn't make it planned, but it does make it rare. What's troubling is how narrow some of these thresholds are.
If Earth were a little closer to the sun, the oceans might boil. A little further, and they might freeze. If gravity were weaker, the atmosphere might escape. Stronger, and the planet might collapse into something uninhabitable.
If the chemical properties of water were different, even slightly, cells might not stick together. If DNA didn't fold the way it does, replication would be unstable. If the meteor had struck 30 seconds earlier or later, the extinction pattern might have been different.
When a system is working, it's easy to overlook dependencies. The supporting parts fade into the background. But when you break those parts apart and examine them, it becomes clear how much had to happen to make the current version possible.
Not perfect, but stable. Not ideal, but viable. The term fine-tuning is often used here, but it implies intent. What is observable is precision, a convergence of variables that seems remarkably consistent.
Not because each part is exceptional, but because their interrelationships, time, chemistry, physics, events, all align in such a way that leaves very little room for error. And yet the system holds together. It evolves, it changes, it breaks and rebuilds, but it does not collapse.
Earth's history is full of accidents, extinctions, collisions, reversals, shifts, and somehow these same events create new structures, more diversity, new paths, greater complexity. It's not that accidents are rare, it's that they continue to resolve themselves in ways that allow life to continue.
Sometimes subtly, sometimes astonishingly. Long before telescopes, genetics, and data models, people looked at the world and asked where it came from. They saw the stars move across the sky. They observed storms, seasons, life, and death.
And most of all, they noticed patterns, cycles, things behaving consistently, repeating themselves over time. And when confronted with a pattern, the question that usually follows is, who or what made it that way? The earliest answers were personal.
Gods, spirits, ancestors, forces with names, intentions, and stories. In these systems, the world was more than just a place. According to the newsroom, we were presented with something created.
Mountain ranges, rivers, the sun and moon, animals and people, all were shaped by invisible entities acting with a purpose. Sometimes that purpose was benevolent, sometimes chaotic. But in either case, it gave events meaning. A drought wasn't just a weather phenomenon, but a message.
A gift wasn't just luck, but a sign of favor. These ideas weren't random. They arose from a desire to understand something greater than the individual, something that moved according to rules but also responded to behavior.
Although modern science has replaced these explanations with models based on observations and testable predictions, the fundamental impulse to search for the agent behind structure has not disappeared. It has simply shifted format. In ancient cultures, design was associated with the divine.
A complex object implied a creator, and a beautiful form implied intention. This can be seen in Greek philosophy, where some thinkers imagined a first cause, a shaping intelligence.
It can be seen in Eastern traditions, where the world is viewed not just as a product, but as an unfolding system, deeply ordered. And it can be seen in religious texts and stories, where creation is intentional, even personal.
Later, with the rise of monotheism and formal theology, the idea of design acquired a new language. Creation from nothing, the purpose, the divine will. The universe was not simply formed, it was chosen. It had a beginning, a purpose, and a structure.
This view dominated for centuries not only religious life, but also scientific thought. Early naturalists often saw their work as uncovering the mind of God through the study of nature. Then, in the 19th century, Darwin proposed a different model, devoid of foresight.
Evolution by natural selection described how complex organisms could arise from simple beginnings through variation and filtration over time. This was a major shift not because it denied design, but because it eliminated the need for it. Biological order could be explained without invoking intention.
This didn't answer all the questions, but it shifted the framework. Since then, science has advanced even further in this direction. According to the conventional view, systems, be they biological, planetary, or cosmic, can emerge from the interaction of rules, matter, and time.
Complexity emerges from simplicity, not through construction, but through self-organization. At each stage, the process is local. There is no central control, only feedback, selection, and iteration. But even within this model, a sense of design remains.
Not in the traditional sense, not like a watchmaker in the sky, but in the structure of results. The brain behaves like a computer, the genome like a script, the laws of physics like a programming interface.
These analogies are not perfect, but they are persistent. We constantly find systems that remind us of the systems we create. And lately, this loop has tightened because we no longer simply describe biology in engineering terms. We build biological tools using engineering.
We write genetic code. We model ecosystems. We develop digital organisms inside algorithms. We build models that design other models.
And in doing so, we begin to see how the line between natural and artificial design is blurring.
Artificial intelligence, once a speculative concept, now writes, draws, translates, predicts. It does not think like humans, but it processes structure. It finds patterns, and sometimes finds solutions that surprise even its creators. Algorithms evolve. Neural networks adapt. Complex behavior emerges from simple rules.
Sound familiar? This doesn't mean algorithms are divine, but they have forced us to ask a new question. Is design always conscious? Does order require intelligence or simply a set of conditions?
If a machine can create something meaningful without understanding it, then perhaps understanding isn't necessary for construction. And if nature can create structure without intention, then perhaps intention isn't the only path to complexity. This is where the conversation has come to.
Not between science and religion, but between different models of emergence. Some say the universe self-organizes. Others say it was formed. But both sides agree that the results are structured. This structure can be described, analyzed, reproduced, sometimes even predicted.
And it extends deep, from physics to chemistry, from cells to consciousness. Over time, the way people talk about this has changed. We no longer imagine the world as constructed by hand. We talk about systems, about constraints, thresholds, probabilities.
The basic idea that function determines form and form indicates cause still drives much research. It manifests itself in everything from simulation theory to the search for extraterrestrial intelligence. If something works too well, we look for cause. The difference now is one of scale.
Ancient explanations remained confined to earth. Rain gods, fertility gods, war gods. Now the questions extend much further. Was the universe itself configured to support life? Are there other configurations in which life is impossible?
Are we the result of random sorting? Or are we in a scenario that favors observers because only observers can notice? This idea, the entropic principle, doesn't answer the question. It merely refreezes it.
If you're in a universe where life exists, it's not surprising to find that you can observe it. But that doesn't explain why the universe allows observers to exist at all. And so the cycle continues.
From gods to algorithms to the simulation hypothesis, every version of the question returns to the same thing. The results look like something that works. Not always perfectly, not always smoothly, but with a level of precision, integration, and synchronization that is hard to ignore.
It all started with a metaphor. We described the brain as a machine, DNA as code, a cell as a factory. These comparisons weren't literal, but they helped explain things. They offered structure, a way to represent what couldn't be seen directly.
But over time, metaphors began to look less like illustrations and more like mirrors. As our digital systems became more complex, they didn't just resemble biology, they began to behave like it.
Simulations started small. A few rules, a few moving parts. A digital ant following a scent trail. A flock of virtual birds lining up in flight. But even in these early experiments, something interesting was happening. Complex behavior emerged from simple instructions.
Not because it was programmed, but because the conditions allowed it. Interaction created emergence. This principle now underlies everything from video game worlds to climate models. We input data, define constraints, and press the Run button, and the system responds.
Sometimes it surprises us, sometimes it fails, but more often than expected, it behaves in a way that feels familiar. Populations rise and fall, cities form, language evolves, artificial agents develop strategies we didn't write.
Not because they understand, but because they are underpinned by mathematics. Simulations don't create real worlds, but they can approximate them. They allow us to see what might happen if a variable changes. Temperatures rise, genes mutate, resources become depleted.
And because of this, they have become more than just tools. They have become thought experiments. Not just what is, but also what could be. And at a certain point, the gap between the model and reality begins to close.
Now it is possible to simulate evolution itself. Digital organisms with virtual genomes mutate, compete, adapt. They develop locomotion, sensory patterns, and even cooperative behavior. No one tells them how. They discover what works through trial and error.
And because computers don't tire, these cycles run thousands of times faster than in nature. Evolution is compressed into hours. In some cases, the solutions they find are unfamiliar, suboptimal from a human perspective, and inelegant, but effective. Algorithms don't seek beauty.
They seek success within the rules they're given. And sometimes the things they produce, shapes, sequences, strategies, reflect patterns found in the natural world. Spirals, branches, cycles, fractals, not copied, but rediscovered. This echo raises questions.
If digital systems with minimal input gravitate towards certain forms, what does that say about those forms? Are they simply efficient? Or is there something deeper, some underlying geometry that all systems, biological or artificial, fall into when given the chance?
The idea of simulation goes even further. Some have suggested that our own universe might be a simulation, not figuratively but literally, a digital environment running on a substrate we can't observe. This idea is no longer science fiction.
It's a philosophical hypothesis advanced by physicists and computer scientists. If simulation advances far enough to simulate consciousness, scientists believed there could be far more simulated realities than real ones, and statistically, we could be in one of them.
There's no direct evidence for this, but there are oddities. Limits in physics that look like resolution, discreteness in matter and energy, observations that cease only when measured, boundaries that resemble calculations more than continua. These could simply be features of the physical universe.
Or they could be artifacts, signs that the system we live in has edges, rules, shortcuts. Even if the idea of simulation is wrong, it has a benefit. It forces us to look at things in a new way.
If reality behaves like a system, we can study it as such. We can analyze its rules, map its parameters, search for consistency. We don't assume a goal, we recognize structure. Virtual reality adds another layer.
We now create digital spaces so immersive that the brain begins to perceive them as real. Games, learning modules, design tools, all of these simulate environments that don't yet exist, yet produce meaningful experiences. In these spaces, perception becomes the primary variable.
If the brain embraces this, the distinction between reality and simulation begins to blur. And within these same systems, we now deploy agents, artificial intelligences that learn, respond, and adapt. These entities don't think like humans, but they process information. They explore options.
Some even begin to exhibit behaviors that mimic learning, not in a conscious sense, but in the search for patterns. It's not hard to imagine a near future where simulations are run not only for prediction, but also for exploration.
A world where we create new chemicals, test new drugs, and develop new designs. All of this within digital frameworks, and where the systems that find these solutions weren't coded line by line, but trained, shaped, and guided by selection.
This is where the boundary between programming and nurturing, between architecture and emergence, begins to collapse. It's not that this replaces old questions, but that it reframes them. If reality can be simulated, even partially, the distinction between design and discovery becomes thinner.
Perhaps design is what happens when conditions favor certain outcomes. Perhaps discovery is simply recognizing what the structure already allows. Simulations don't have to be perfect, but if they produce systems that work, respond, and adapt, then perhaps they offer a kind of parallel creation that we understand better, not by asking who built it, but by watching it unfold.
From the newsroom, if something looks structured, it's natural to ask whether it was designed that way. But the next question is harder. If it was designed, then why exactly? Because this version of Earth isn't perfect. It works, mostly.
It clearly supports life, but it's also uneven, fragile, full of blind spots, compromises, and strange decisions. Bodies wear out. Ecosystems collapse. Natural disasters kill without warning. The same systems that enable growth also allow suffering. If it's design, then it's not pure.
And that raises the possibility that it's not designed as humans conceive of it. The idea of a designed world usually comes with the assumptions that things are made for a purpose, that there's a best-case scenario, that problems are exceptions, but nature doesn't follow that logic. The most successful systems aren't the most elegant. They're the ones that survive long enough to matter, which often means those that are just good enough, not perfect, just stable.
There are parts of Earth that seem built to support life. The atmosphere, the slope, the presence of water. But there are others that seem more indifferent.
Earthquakes, viruses, genetic diseases, predators that evolve faster than prey, prey that suffer without evolving at all, extinctions that wipe out entire branches of life before they have a chance to adapt. These are not flaws in a blueprint.
They are the peculiarities of an open process. Even the human body, so often described in terms of precision, has structural compromises. The spine, inherited from creatures that walked on all fours, struggles with the demands of an upright posture.
The eye has a blind spot where the optic nerve exits the retina. The trachea and esophagus share a pathway that leads to a constant risk of asphyxiation. The brain, despite all its capabilities, is prone to distortions, addictions, delusions, and degeneration.
From the news editors, evolution explains this. Structures adapt slowly, often through reuse. A solution that works is copied and modified, not redesigned from scratch. This leads to inefficiencies, overlapping functions, unnecessary complexity, and vestigial organs, but it also leads to flexibility. A design that's good enough doesn't need to be optimized. So, if we're talking about design, perhaps it's not the kind we're used to. From the newsroom, not planned in advance, not directed by a single goal.
Perhaps it's more like an emergent architecture, shaped by constraints, feedback, and chance. In this framework, the question, why is it like this, becomes, why does this version continue to survive? Which is a completely different question. There's also the issue of scale. Some patterns appear chaotic only up close. Zoom out, and the jagged edges merge into structure.
Climate systems fluctuate, but over long periods, they stabilize. Ecosystems collapse and then rebuild around new species. Genetic diversity creates vulnerabilities, but it also creates resilience.
Life as a whole lasts for billions of years. This is not a sign of perfection. It is a sign of longevity, but it still leaves room for surprise and discomfort.
For despite all the systems that seem precisely balanced, there are just as many that seem arbitrary. Why does reproduction depend on chance? Why do beneficial mutations take so long to spread? Why are so many parts of nature locked in cycles of brutal famine and competition? The answer, from a design perspective, may be that suffering is not a flaw, it's part of the mechanism. Pressure drives adaptation. Scarcity drives cooperation. Failure drives novelty.
But this explanation carries weight. It implies a kind of moral distance, a system that works by allowing parts of itself to break down. People tend to imagine better versions, a world without pain, without aging, without extinction, a body that fully regenerates.
A planet without tsunamis or drought. In these imaginary worlds, the question is inverted. If Earth was designed, why wasn't it made more like them?
The answer might be that trade-offs are inevitable, that complexity requires risk, that evolution, or any self-modifying system, cannot be tightly controlled without losing its ability to grow. But this is an assumption. It presupposes goals. And the patterns we see clearly don't point to one. They point to survival, not direction. In technology, humans design systems to achieve specific goals: speed, efficiency, safety. But nature doesn't optimize in these terms. It adapts to what works under pressure. This means that some things are elegant, others clumsy. Some parts are ancient, others improvised. The brain is powerful, but also vulnerable. The immune system is adaptive, but also reactive. Intelligence allows for planning, but also for anxiety.
There's no consistent theme, no single idea that ties it all together, only a history of forms that seem to build on what came before without completely resetting. If there is design here, it's not centralized, it's distributed, multi-layered, perhaps even unconscious.
The idea that the Earth was designed doesn't require it to be perfect. But the reality we see, full of beautiful systems that sometimes fail in brutal ways, suggests that if design is present, it operates by different rules, not by human logic, not by human goals, perhaps not even by human values.
It's also possible that we're asking the wrong question, that design and chance aren't opposites, that structure can emerge without imposition, that feedback, replication, and memory are enough to create the appearance of intention. Within this framework, the question, why is it like this,
becomes less about meaning and more about consequences. Not who chose it, but what made it sustainable. In every system, no matter how detailed, tested, or well-modeled, there comes a point when explanation ceases.
Not because there's nothing more to know, but because our tools have reached their limits. And when that point arrives, something else moves. Sometimes it's silence, sometimes it's questions, and sometimes it's faith. Science works by building boundaries, measurable, repeatable, observable.
It deals with what can be tested. Gravity isn't a theory because someone believed in it, it's a theory because it predicts what will happen next. The same with thermodynamics, evolution, electromagnetism. The power of science isn't what it says about meaning.
It's how well it predicts. But people don't live by prediction alone. They live by story, purpose, connection. And when these things can't be found in equations, they often lie elsewhere. in frameworks that offer more than mechanisms, that speak in terms of why rather than how.
For some, this is religion. For others, philosophy. And for many, a mixture of both. A tradition shaped by culture, family, language, and history. Systems of thought that help explain not only how the world works, but what the world means.
These systems don't disappear with the progress of science. They evolve alongside it. Advanced physics, in any case, is beginning to resemble philosophy. Quantum mechanics describes more than just particles. It describes probabilities, observation, uncertainty.
General relativity doesn't just explain motion, it rewrites the shape of space and time. These are not intuitive ideas. They stretch the boundaries of human language. They resist visualization. But they are real, confirmed by experiments, embedded in technologies that guide our understanding of the universe.
And yet, even these models falter. We lack a unified theory that unites gravity with quantum mechanics. We don't know what dark matter is. We don't know why the constants of nature have the values they do, why the charge of the electron or the strength of the nuclear force fit precisely into the blueprint that allows atoms to exist.
These aren't minor flaws, they're fundamental gaps. Into these gaps, people inject meaning. Some say the universe simply is. There's no deeper reason, no hidden message, just a structure that happened to work, a roll of the cosmic dice that landed favorably for life.
Others see intention, not necessarily in the details, but in the fact that anything exists at all, that laws operate, that intelligence emerges, that order repeats itself in ways that allow for thought.
None of these perspectives can be proven, and none of them need be. They're not models in the scientific sense, they're lenses, ways of interpreting what science observes.
What makes this space between science and faith interesting is how many of the same questions exist in both. What is time? What is consciousness? What existed before the beginning? Where does order come from?
These are not spiritual questions by default, but they become spiritual when the answers become values, identity, responsibility, purpose. Even faith in science requires a certain trust, not blind trust, but trust in method, in honesty, in the assumption that reality behaves consistently, that measurements matter, that cause and effect are more than illusion.
This is not faith in the supernatural sense, but it is still fundamental. Science does not prove itself from the outside. It is a system that works because it assumes that the world is knowable.
Faith, in its many forms, works differently. It does not require observation. It perseveres when the evidence runs out. It offers a story where the data ends. This does not make it any less real. It makes it suitable for a different kind of question.
For most of human history, science and faith were not separate. Early scientists were often driven by religious motives to uncover the mechanisms of creation, to see God's hand in the laws of nature.
Only in the last few centuries have the two come to be seen as opposites. In practice, most people don't live strictly within one or the other. They live in a mixture, trusting science to describe the how, while turning to other systems to ask the why.
The interesting part is where they intersect. When faith attempts to make scientific claims, it often conflicts. But when it speaks in metaphors, mysteries, or meanings, it fills in the gaps science fails to address.
And when science enters these same spaces, speculating about multiverses, simulations, or the nature of consciousness, it begins to sound like faith itself. This isn't a failure. It's a testing of boundaries, a sign that curiosity continues even after the model ends.
Many physicists acknowledge this openly.
They describe the laws of the universe as elegant, wondrous, or beautiful. They speak of simplicity beneath chaos, of symmetry breaking that blurs into complexity.
They use words like finely tuned, not to imply a tuner, but to describe how narrow the window between a dead universe and a living one is.
Others look at the same data and see randomness, an ocean of possible outcomes in which this one just happened to work. The anthropic principle, we observe a life-supporting universe because only life-supporting universes produce observers, doesn't explain why, but it explains why we do.
Yet the question remains, is the precision we see a fact of nature or a reflection of how we interpret it? Are we reading meaning into structure or uncovering meaning that's already there?
That's where faith comes in, not to answer definitively, but to suggest, to imagine, to crack open a door. Not everything needs to be resolved. Some parts of life are better lived with unanswered questions. Which brings us to the end, though not the conclusion.
The news editorial team presents. The ultimate question isn't whether the Earth was designed or by whom. What matters is how we exist on it now, using the systems we inherited, the atmosphere, water resources, the passage of time, patterns, chance, the ability to think, imagine, and create.
The question of the world's origins never truly disappears. It simply fades for a time. In the flow of work, the bustle of the city, the routine of habits, it recedes into the background.
But then something brings it back. The night sky, a fragile, fossilized remnant, a perfectly timed event, and here it is again, lingering in the background. Is all this something we found, or something we were destined to find? Designed or discovered? Created or emerged?
These two concepts have different roots, but often converge at a single point, the edge of what we can explain by looking outward. If Earth is a project, it is the most complex project we have ever encountered.
Every molecule is precisely positioned, every cycle balanced, every feedback loop delicately integrated into the next. It is a system that has sustained itself for billions of years, that processes and transforms, that allows not only survival, but also learning.
This in itself would be a miracle, not a spectacle, but a miracle of quiet structure. And if Earth is not a project, if it arose spontaneously through the slow interplay of physical and chemical processes in time, then that is no less astonishing.
For in the end, it discovered itself, a planet that gained consciousness, a process that closed and saw itself, life that learned to ask questions. In either case, the result is the same. We are here, thinking, observing, wondering, creating tools, finding meaning, creating stories.
We study cells, galaxies, equations, and ourselves. We make maps not because we are commanded to, but because we need to know where we are.
And we are not simply here physically, not simply on a rock orbiting a star, but fully here, conscious of the conditions that allowed for awareness to emerge, able to reflect on what came before and imagine what might happen in the future.
Whatever this is, it is rare, and perhaps that is enough to cling to it, even if its origins remain unsolved. Perhaps power does not lie in knowing the answer.
Perhaps it lies in the ability to ask questions, because systems continue to function regardless of ultimate explanation. The rotation of the Earth, the gravitational pull of the Moon, the breathing of the atmosphere, the rise and fall of ecosystems, the ceaseless dance of genes, memory, and environment.
The rules have not changed, but now we see them.
And seeing them does not require certainty. It requires only presence, attention, a willingness to acknowledge that some things are structured, unusual, and astonishing.
Not because they were created for us, but because we are capable of seeing them at all. It could be intentional. It could be an accident. But either way, it's a discovery. And it's still ongoing. The news team thanks you for taking the time to be here, not rushing, not trying to achieve anything, but simply being with a question that doesn't necessarily need to be solved to be worth asking.
Whether the Earth was designed or discovered, whether these systems are intentional or spontaneously emerging, the world remains no less wondrous. And you, the listeners, the breathers, the mindful, are also part of this system.
Good night, or long ponders. There is no pressure one way or the other. The planet will continue to turn, the patterns will continue, and the good questions will still be here in the morning. Good night.